Hello. There are if the speaker. I think Professor Bergnieri, if you're around, you want to check your slides.
Yes, sure. Good morning.
Good morning. Hi. Let's check it quickly. Yeah, it's visible. The transitions are fine. Yeah, I can see your pointer as well.
Okay, perfect.
Okay, thanks. So welcome everyone to the post-lunch session. In this session, we'll have 3 talks of half an hour duration each, followed by 5 minutes of Q&A. So Professor Bagmiani, I will remind you in the last 5 minutes of your talk.
Yes, please.
Yeah, so maybe we look for a couple of minutes.
Okay, maybe let me introduce the shared person.
Okay, sorry, I should have introduced myself. Don't worry, I can introduce myself. I am Anumitra Mukherjee. I am a condensed matter theorist working in National Institute of Science, Education and Research, Bhubaneswar, India. So I'll be the chair for this session. Yeah.
So Mukherjee, you are also requested to get information from the speaker.
Yes. Yeah, please go ahead.
So you please get confirmation from the speaker whether we can record their talks or not. So
Yes, so that I should do at the end, right? Or I can do it now.
Because by default it is recording. So if they tell that they are not comfortable, then we do not record their talks.
Okay, so
I am okay with recording their talks.
okay. So Professor Bagmiani, you're okay with your talk being recorded?
Yes, it's fine. Yes.
Okay, thanks. Yeah, so welcome everyone. So the first talk of this session is by Professor Maya Bagmiani from Max Planck Institute of Chemical Physics and Solids. The title of the talk is From Theoretical Predictions to Material Realizations of Topological Semimetals. So Professor Bagmiani, please, the floor is yours.
Okay, thank you very much for inviting me to give this talk. And I'm very sorry I cannot be in India because I would really like to go to India. So as the chairman said, I'm going to talk about how we go from pure theoretical mathematical prediction to the experimental realization of topological semimetals. So basically, it is done in 3 steps. We do a classification of topological phases in terms of topological invariant and crystalline symmetries. Then we do ab initio calculations to see whether we can reproduce these mathematically predicted electronic properties in real materials using first principles calculations, and then we collaborate with experimentalists or more phenomenological physicists to actually find experimental signatures of these systems. So this is going to be the outline of my talk. As I said, I'm going to talk about semimetals, topological semimetals. There are different types of topological semimetals. I'm going to start with the Weyl semimetals and the idea of Weyl semimetals and nodal line. Then how can we find these materials, these topological objects in real materials, performing high throughput calculations. And for that, I'm going to introduce the formalism that we use, topological quantum chemistry. I'm going to talk about generalization of topological semimetals to high order nodal points and also in magnetic materials. And then I will discuss some experimental realizations. Okay. So electrons have a mass, and because they have a mass, their dispersion have a curve. However, almost 100 years ago, Hermann Weyl canceled out the mass in the Dirac equation, and he predicted the existence of fermionic excitations with linear dispersion, which means they are massless. These Weyl fermions have been searched for many years because, of course, if we find fermions that are massless, this will revolutionize technology since there will be no power dissipation. However, particle physicists fail to find these Weyl fermions in their accelerators. I think at some point neutrinos were proposed, but whether neutrino has a mass or not is under discussion. And so the search for a Weyl fermion in the particle physics community is still ongoing. However, we could actually find a quasi-particle excitation of a Weyl fermion in condensed matter physics. So we can mimic the environment of a crystal in a way that the dispersion of the electron within the crystal is linear, and they behave as if they had no mass. Of course, this is bounded to the brilliance zone, and they do not travel at the speed of light, as Hermann Weyl predicted. They are bounded by the momentum k, and as I said, they are quasi-particle excitations in a sense that they only have this dispersion and this massless property within the crystal. If we take it out of the crystal, the electron acquires a mass and it has a dispersion. But these Weyl fermions within crystals are very interesting. They always come in pairs, and they act as a source and sink of Berry curvature. So depending on the chirality of the Weyl, one is a source of Berry curvature and the other one absorbs it. And because of these properties, they have a very particular surface states that can be predicted from the bulk that are called Fermi arc, and the surface state connect these two Weyls, and they are very robust as they are protected by topological order. So the minimum number of Weyls that one can find in a crystal is 2, and this only happens when we break time reversal symmetry. So it would be really interesting for technological applications to actually find a single pair of Weyl points near the Fermi level, free of other energy windows. This is what we call the ideal Weyl crystal. There has been several proposals in the past years. Here we have a very interesting table made by Jean Rousseau. And so here we have the proposed crystals, the pair of Weyl nodes, the Fermi level, how close far are from the Fermi level, and the number of irrelevant bands. So, so far, there has not been proposed an ideal Weyl that actually has only a pair of Weyl crossings in the Fermi level without more irrelevant bands. The closest one was this alloys, but actually it was actually difficult to grow. At the same time, there is other topological object that has non-zero Berry phase, and but instead of being a point, they are lines. So they have like the multiple crossings along a line in the brilliance zone, and they have a non-zero Berry curvature, and these are called nodal lines. Nodal lines are more difficult to detect because it's not clear whether they have an experimental signature in the surface, and it strongly depends on the symmetry that protects the line. So if we have another line in a plane where mirror symmetry is preserved, we will only find experimental signature in the surfaces where the mirror plane is also preserved. And these experimental signatures are called Brownhead states. So we want to find materials that actually either display Weyl nodes because they have this very interesting surface state, or nodal lines because nodal lines are in general quite flat and they would be very interesting for correlations or superconductivity. Okay, so how do we look for them? So in order to look for them in a high throughput way, we're gonna use formalism developed 5 years ago that is called topological quantum chemistry, and it has been extended recently to magnetic phases. The reason why we want to look for magnetic materials is because, as I said, we only find an ideal Weyl semimetal whenever we have time reversal symmetry broken, so therefore we need to have an intrinsic magnetic moment. So topological quantum chemistry is based on a mathematical tool developed by Michel and Zach several years ago that is called elementary band representation. So elementary band representation is actually a set of bands that can be predicted from real space, and this set of bands that are predicted from real space are actually connected in reciprocal space. So if we look here, we do have the honeycomb lattice, right, with two inequivalent sides in the lattice. And if we place PC or PX or PY orbitals, this combination of the orbital atomic site and a lattice, which will be PC orbitals, atomic site is the 2b Bykov position, which is the site of the honeycomb lattice, and the lattice is the hexagonal space group. This combination of these three ingredients lead us to a set of bands that are connected in reciprocal space. And this set of bands are uniquely defined by the irreducible representation of the little group at the high symmetry points, okay, for this space group. So the statement that Mr. Sell and Zach made is that whenever these three ingredients define an elementary band representation, which means that these bands are connected, dictated by group theory, whenever we have these three ingredients, the bands are going to be connected in reciprocal space. Now, this is always true, but it's only true if our bands are not topological, because when our bands are topological, what happens is that the set of bands that should be connected in reciprocal space are split. And in that splitting, the charge in real space moves away and we get a topological gap. In order to understand this part, we need to use the compatibility relations. So the compatibility relations tell us how bands are connected in reciprocal space. So for example, gamma 8 and K6 will be connected if the line that connects them is a subgroup of gamma 8 and K6 at the same time, which means all the connectivities in reciprocal space are also dictated by group theory. Which means that whenever we have the possibility of swapping irreps, because this formalism is about qualitative approach and not energetics, so nothing avoids an irrep to swap with another one. Whenever this irrep swap, and we are allowed to open a gap, this gap will be topological. So what we need to do actually in order to, in order to perform a high throughput search is calculate the irreducible representation of the wave function at the high symmetry point and then look at the compatibility relations. So our DFT calculations are way faster than calculating the full band structure because we only need to know what happens at the high symmetry point. So performing this high throughput search, we found of the order of, we check of the order of 50,000 materials, and within these 50,000 materials, we saw that one can find that roughly half of them display topological features in one way or another. So this means that there is a lot of room to look for potential topological materials, and that this method is actually very effective and fast. Okay, so now we want to find topological magnetic materials that are semimetals, and for that we're gonna use the same method, but we're gonna extend it to magnetic phases. So what I have explained you before, the work started in 2017. However, it took us 4 years to actually extend the method to magnetic systems. Why? Because there were no magnetic representations. So we have the reducible representation of the high symmetry point for non-magnetic system, but for magnetic systems, there weren't such representation. They were not tabulated. They were a book by Bradley and Cracknell, but still it was very difficult to read. So we had to actually calculate all these co-representation. There were no magnetic codes that keep actually the symmetry of the crystal. We have VASP, and VASP considers the magnetic moment to calculate the wave function, but then it doesn't keep the symmetries itself. So we need to implement an interface to actually add all the symmetries of the magnetic groups. And there was no magnetic topological classification in terms of irreducible representation. And this was also needed to be implemented. So when these 3 steps were done, and it took, as I said, several years, a high throughput search of magnetic materials was able to be carried out. And all this information is in the Bilbao crystallographic server in the URL that I put here. Okay, so now we needed to do first principle calculations, and this was actually quite tricky because, as we know, it's very difficult to calculate by first principle the ground state of a magnetic system, owing to all the possible combinations that one can find, and also because in magnetic system we might have correlations, and correlations can be interpreted with DFT using U, but then you need different values of U. So the first obstacle was overcome by just considering magnetic materials that actually have a magnetic phase defined by a neutron scattering. So we took only experimental data of magnetic materials that have been, whose phase has been, let's say, defined experimentally. And for that, we use the Bilbao crystallographic server database. So in this sense, we did not perform any relaxation of the ground state because we wanted to keep the magnetic phase of the experimental data. As for the problem of U, what we did is calculate the same band structure for different values of U. In a sense that if you have, for example, the electrons in a crystal and we calculate the band structure for U equals 2, 4, 6, and then it happens that for whatever reason, your magnetic moment lies between U4 and U6. If for U4, between U2 and U4 is for U2, your phase is topological, and for U4, your phase is topological, then between that range of U's, you have many chances of finding a topological phase. So, and then we perform a topological classification. So, it was divided in six phases: insulating phases with atomic insulators, which are trivial phases, and for semimetals. These are topological semimetals, and we divide it into types with Fermi degeneracy, means that they have crossings at the Fermi level, and then for semimetals, where the crossings are away from the Fermi level. Smith index semimetals. This is a new type of semimetals that have somehow the crossings away from the high symmetry lines, so anywhere in the region zone, but we can identify them by looking at the eigenvalues. And then we have stable topological insulators and fragile topological insulators. So using this classification and performing a high throughput search in the same way as we did for non-magnetic materials, we found 103 new magnetic materials with non-trivial topology for certain values of U, and among them of the order of 50 that are topological for every value of U that we chose. We selected some materials that actually look very interesting, for I'd say experimental realizations. This is an anti-ferromagnetic topological insulator. This is a very interesting topological semimetal. I think this one was also a ferromagnetic topological semimetal. And as we see, we can find very clean band structures and interesting materials. And we also upload all these materials in a branch of the Topological Quantum Chemistry database for magnetic materials, where one can find the band structure, topological analysis, and all for the different values of U that we used. Okay, so this was a general search, and as I said, we can identify topological semimetals, but then if we want to go for further analysis, we need to actually look in more details at those topological crossings. So as I said before, we are interested in ideal Weyl semimetals that are close to the Fermi level. But these ideal Weyl semimetals actually happen anywhere anywhere in the region zone, because they don't need to be protected by any type of symmetry. Therefore, they are not that easy to find. And it's not that clear how far they are from each other, in a sense that we can find a very long Fermi arc or a very short one. And this is another obstacle that we want to overcome. And for that, we look for high order nodal points that actually are pinned at the high symmetry points. How do we look for them? Well, at the high symmetry points, the dimension of the crossing is given by the dimension of the irreducible representation. So that was not very tough to find because we have all these tables now. But then looking at the crossings, we need to analyze also the topology. And what we found is that for systems that actually lack inversion of mirror symmetries, the improper operations, let's say, that are defined by only pure rotational symmetry, what happens is that we can find these high nodal crossings at the high symmetry points and very large Chern numbers. And more than that, what happens is because there are no inversion or mirror in the crystal, we can go from one high symmetry point to its time reversal counterpart with a very, very long Fermi arc, as we can see here. This Fermi arc is traversing the full brilliance zone. So this is actually incredibly interesting for any type of application, because you have this very robust surface state protected by topology, predicted by bulk, and they are really large. So we perform a classification of all the chiral space group that we can find for non-magnetic materials at the beginning, and this can be found in this paper, and actually the experimental signature that they can present. Like the linear photogalvanic effect, circular photogalvanic effect, and the matrix elements, if anyone is interested, is here. And once the classification for non-magnetic materials was done, we moved to magnetic groups. So as I said, magnetic groups are more complicated, and to look at the dimension of the irreducible representation, we need to consider not only the crystalline symmetries that we find in real space, but also combination of real symmetries with time reversal symmetry. So in a magnetic group, time reversal symmetry by itself can never exist, but it can be combined with other symmetries like mirror or translation or rotations. And this makes that the number of magnetic groups is way larger than the number of non-magnetic groups. So we go from 230 space group to 1600 magnetic groups. So in order to look at the dimensions at the high symmetry points, we use the classification of magnetic materials in terms of type 1, type 2, type 3, and type 4. So type 1 are the ones that just have a time reversal symmetry broken. So we start from a non-magnetic system like this one, and spin up and spin down, or J1 and J, I mean, the opposite spins are not tied by time reversal symmetry. It breaks and they split. This is type 1, and type 3 and type 4 is when we have a time reversal symmetry combined with a translation. So for type 3, the translation are not fractional, and for type 4, translation are fractional. And the reason why we did it in this way was because we follow the algorithm by Briley and Cracknell, where actually they are able to relate the brilliance zone of the type 2 with the brilliance zones of the different type 1 and type 3 and type 4. And like this, we were able to actually build another table looking at the dimension of the irreducible representation. So for type 3 and type 4, we find that actually we can find these high order nodal points that actually, if they are non-chiral, they reproduce the same properties as the ones that were non-magnetic. So they also have these very long Fermi arcs, which is incredibly interesting because now we have a very long Fermi arc traversing the brilliance zone, and it's spin polarized. And looking in the literature, we found that this compound actually in P213 in the antiferromagnetic phase, and very particular antiferromagnetic phase, because it needs to preserve the cubic crystal system. So what it has is these triangular nets coming out from the manganese. Here we have the band structure without magnetism, and here we have the band structure with this antiferromagnetic phase. We find very interesting 3-4 crossings at the Fermi level that actually display large Chern numbers and large Fermi arcs. Okay, and now in the last minutes, I want to discuss some experimental realizations. So I want to convince you that an ideal Weyl candidate under magnetic fields is European cadmium arsenide. So European cadmium arsenide has an hexagonal lattice, and in its ferromagnetic phase, it displays only 2 Weyls at the Fermi level that that actually are free from other energy bands. So the ground state of European cadmium arsenide till very recent, because there will be some papers coming out soon, it was antiferromagnetic in the out of plane. And if we calculate the band structure, what we see is that here we find a gap. However, under the presence of a magnetic field, we can align the magnetic moments in the direction of the z-axis. And when this happens, what we find is that we see, because of Zeeman split, bands split, and we see this very nice closing close to the Fermi level. If we zoom in, this is for the antiferromagnetic phase, and this is for the ferromagnetic phase. Okay, so as we see, we have 2 Weyls very close to the Fermi level, separated, unfortunately, a small distance. So to make sure our DFT calculations were correct, we compare our antiferromagnetic phase with ARPES experiments for several values of U to actually choose the correct U. And what we found is that for U equals 6, I think, we could reproduce the ARPES data. And here we have the F electrons, and here we have the F electrons predicted by DFT. Okay, there were also performed energy cuts where we actually see properly the dispersion of the antiferromagnetic phase as was expected from the DFT calculations. And then in order to prove that we actually have 2 Weyls, transport measurements were performed. So Shushnikov, the Haas oscillation were measured. And what we saw is that both the oscillations and the effective mass, that is very small, actually corresponds to what would expect for a Weyl semimetal. So European cadmium arsenide, we believe, is a very strong candidate for an ideal Weyl semimetal. Another material that also displays these very interesting topological semimetallic properties is the pyrite cobalt disulfide. So in the absence of magnetism, we see this is the band structure that looks chemically unstable. However, if we add magnetism, the band structure and the chemical stability change. But as I said, we need to actually first figure out what is the Celto potential and the value of U we need to use. And in this particular compound, this was very interesting.
Excuse me, Professor Bergman, 5 minutes more.
Yes. Thank you. In this particular case, it was very interesting because it happens that even though it's a magnetic materials and one would expect correlations, what we found is that the best matching first principle calculations were for local density approximation for U equals 0, which means that this type of pyrite, what it represents, what it displays is stoner magnetism. So how did we figure out this? We figured out this because in the ARPES measurements, we found these pockets at the R point where whenever we used U equals 3 and GGA, which is the most obvious setup of parameters to use for these cases, the band structures could not reproduce what ARPES measurement were seeing, no matter the convergence criteria we chose. However, if we use U equals 0 and local density approximation, we see that the R point, we find the pocket that the ARPES data was predicting. So this was our parameter setup to actually carry the further calculations and experiment. Yes, we also look at other high symmetry lines, and we could see several features in ARPES and in our DFT calculations, even though the bands were a bit normalized because of some correlations, the features were there. So for some energy guides in the cleavage plane 111 in the bulk case, we also found a very nice agreement. And also for other cleavage planes, we also found very nice agreement between the RPS measurements and the DFT calculation that actually it was very, very nice to see such a nice fit. So, but we wanted we are interested in Weyl nodes and nodal lines. And in the bulk one structure, we could actually see that there were, away from the brilliant zone, some crossings that actually belong to Weyl nodes and also other crossings that belong to another lines. And we wanted to detect these two features experimentally. So if we go from the gamma endpoint, my student Inigo found that we have another line at around minus 0.2, but if we move a little bit away from the endpoint to M star, what we see is a Weyl node. So we wanted to detect these two. And for that, what Inigo and Niels thought is that let's look at different energy cuts, since the Weyl node will only happen in one crossing, but the nodal line, as I said, is a line, so we need to see those crossings in different energy cuts. So this is what they did. They look at the cut plane 111 and 100, and they actually were able to identify both crossings, the Weyl cone that actually crosses a little bit further up, that comes from here, and the line node that actually is exactly in this plane. And then looking at the surface, it was more complicated because in the surface you might have different domains, but still in the gamma X direction, the calculations could see these Fermi arcs going from Weyl node to another one, and actually the RPS measurement could also identify this very strong surface state here that we believe correspond to the Weyl node. Also, looking at energy cuts, theoretically, what we found is that the Fermi arcs that appear for different energy cuts are actually spin polarized, which means this is very interesting for interfaces and spintronics applications. And okay, so since I'm running out of time, I'm going to skip the last part. And I'm going to jump to the summary and conclusions. So I have introduced a search engine for magnetic materials, which is magnetic topological quantum chemistry, and found very of the order of 100 new topological magnetic materials. We have also predict the high order nodal crossings that are very interesting for long and magnetic polarized fermion arc. And then I discussed some experimental materials, and I believe the collaboration between theory and experimental is crucial. And thank you very much for your attention.
Thank you, Professor Bargnani, for the very interesting talk. The session is now open for questions. People can either raise hands and ask questions or can type in the chat box. So I see one. Bahadur, please go ahead. You can unmute and just ask.
Hi, thanks for the nice talk. I missed something you mentioned about Smith index semimetals. I'm wondering how those are different than the Weyl and nodal semimetals we always talk about.
Okay, but when Smith index semimetals, what it's telling you is that because too high symmetry, what it's telling you is that because if looking at the eigenvalues at the high symmetry points, the rifts have been swapped so that you should find a crossing, but you don't know what type of crossing you're gonna find.
Okay,
so it's more general than it's just telling you that there must be a crossing, but you don't know if it's a Weyl or a nodal or a Dirac.
Oh, I see. And moreover, it's a generic A point, if I'm hearing it correct.
Yeah.
Okay. Okay. Thank you.
Okay. Maybe I think I can ask one question. So it's purely a technical question. I don't know whether I can ask you this question or not. This is about the RPS data and COS. So what is that?
Sorry, I cannot hear you.
Can you hear me now?
Yes, I can hear you. Yes.
Yeah, this is a technical question on RPS data, but I don't know. Maybe you might have discussed with the people who did RPS measurements.
Okay.
Maybe I don't know whether you bothered at all about this RPS measurement, because I think you do calculations, right? Or you do ARPES also?
No, I'm a theorist.
You are theorist. So maybe, I don't know, maybe you may explain. So the ARPES data is so lousy on this UAS2, unless you put some DFT calculations, nobody knows what is what there. So why is that?
Do you do ARPES measurements?
Yes.
And you think this is lousy? Because I thought it was very good, but I don't know.
Yeah, especially band dispersions are really lousy, and then unless you put DFT next to it, it's very difficult to say what is what. Exactly, this one.
Yeah,
So,
well, this is why we do DFT. Otherwise, DFT also would not be necessary, right?
I'm also pretty sure. I think you did this ARPES data from PSI. The machine must be very good. So, is this sample problem or?
Okay. The right answer would be I don't know. But from discussions, I think when you have a magnetic crystal and not, I mean, the cleavage plane in this sample is complicated because they are not, I mean, they are very tight. It's not like van der Waals layer structure where you can just cleave it and that's it. And it might also induce different magnetic domains. So that could be one reason why the ARPES data is so lousy. But I invite you to reproduce it.
No. No, we just want, we tried. We tried to grow these crystals. We had seen recently, this paper, and we tried, and then unfortunately my students are not still successful. So that's why we focused on this crystal.
Yeah. Anyway, you can contact Niels Rotter. Is he the one who did it? And I believe that the same growers that gave us the samples will be very happy to send it to you.
Oh.
So just contact me, and I can put you in touch with both of them.
Okay, thank you.
I will be very happy to get better ARPES data.
Yeah. Thanks a lot.
Sure. Thank you. So I don't see any more raised hands. Maybe I can quickly ask a question. In strongly correlated, there are this LDA DMFT calculations for Dirac semimetals, where there seems to be cooperation between correlation and spin orbit coupling, leading to some high mobility, just some Tokura group experiment, as far as I remember. So I was just wondering.
You mean? Sorry.
Go ahead.
No, I thought you were done. No, continue, please.
No, I was asking in the sort of, you have a high throughput sort of materials that you can examine. So are there examples of similar cooperation in the kind of materials or examples that you have found in any?
Of magnetic aerial materials?
Yes,
No, not yet.
Oh, okay. I see. Sure, thank you.
Okay.
Any other questions? I don't see any raised hands. So with that, let me thank Professor Bargnani for a wonderful talk.
Thank you very much. And I hope when COVID is over, I will be able to go to India.
Sure, we look forward.
Bye.
Okay, so after maybe you can try and share the screen.
Yes. Is it visible?
Yeah, it's visible. Maybe just full screen. Maybe just yeah, and maybe you can see your mouse. Maybe just try a transition and you're good to go. Yeah, I can see your mouse, but just can you do a slide transition to see?
Yeah.
Yeah, fine, good. It's all fine. So let me introduce you to the audience. So the next talk is by Professor Aftab Alam from IIT Bombay, and he's going to talk about novel composite quantum material. So Aftab, I'll just give you a reminder 5 minutes prior to the end of your talk.
Yeah, sure.
And questions, people can raise hands at the end. Pressing issues, you can quickly ask if there is any, and chat box is of course open for questions. Please go.
Sure. Thanks, Anamitra. Let me first thank the organizers for arranging this nice platform for topology in condensed matter, facilitating the opportunity to present and listen some of the interesting talk on this core subject. So my talk today is going to be focused on an interesting quantum materials which we have recently studied, the so-called quaternary chalcogenide, Cu2Zn-GT4, which interestingly exhibits multiple coexistent quantum properties, and hence the word composite quantum material. This theoretically predicted material is now being synthesized experimentally by our collaborators to verify our findings. This work is done by two bright scholars, Bhavna Sahni, who's a PhD student, and Shri Parvati, an institute postdoctoral fellow in my group. So just to give a perspective about composite quantum materials, these are unique materials which host more than one distinct quantum phenomena in single system. For instance, magnetism, topological superconductivity, ferroelectricity, Rashba spin physics, spintronics, etc. These are some of the examples of such phenomena which, although are ubiquitously observed in several functional materials and have recently drawn tremendous attention of the community, the coexistence of more than one such phenomena in a single material can actually give a fertile ground to investigate the intercorrelation and hence the governing physics behind them. So, some of the recent literature along these lines, which have explored coexistent phenomena, includes topological non-triviality and superconductivity, which had been found in several materials. This is just one reference over here. There are coexistence of action insulator and churn insulator phase in MnBi2Te4. There are also topological non-trivial property and piezoelectricity found in this indium exomonolayer. Topological non-trivial properties and Rashba spin physics, the Rashba coupling has been investigated also. Then topological non-triviality and spin gapless semiconductors and charge density waves and topological non-triviality. Now, how does one really guess about such coexistence? Apparently, these interconnections are mediated through certain common requirements. For example, crystal symmetry, strong spin orbit coupling, etc. For an instance, the topological insulator and ferroelectricity are shown to couple in polar compounds with strong spin orbit coupling and broken inversion symmetry. TI and Rashba physics require a similar prerequisites. So, there are some studies on thermoelectrics and topological insulator as well, although at a very preliminary stage. Now, it is well known that topological materials, including semimetals, acquire unique band structure, which are potential for unusual electronic transport. If one can carefully engineer the bands of a topological semi-metal, one can help to achieve high thermoelectric performance, because thermoelectric performance are intimately tied to the topology of the bands near Fermi level. For instance, the coexistence of linearized non-trivial Dirac or Weyl bands and regular parabolic bands can help to maximize both carrier mobility as well as thermal power. So one of the motivation behind the present study is to investigate the possibility of composite quantum phases involving topological semi-metal and thermoelectric performance. We have also studied some of the topological phonon aspects as well, which I'll probably come depending on the time towards the end. However, the choice of material is pretty crucial if we really would like to achieve this kind of composite phenomena. So it is known that chalcogenides have gathered enormous attention due to their wide application. For example, solar energy, batteries, thermoelectric devices, as well as topological insulators. So these, conventional chalcogenides have already shown some of these interesting phenomena. There are also quaternary chalcogenides. Some of the studies are there, where people have also found some promise from photovoltaic, electrocatalysis, topological insulator side. Though these studies are ubiquitous, in different chalcogenides, but a more detailed study where both topological as well as thermoelectric applications are being investigated is not there. So what we have done, we have actually chosen a small class Cu2AbX4, which are experimentally synthesized compounds. So there is no question of instability, and investigated them for finding out how their band topology are, whether they are topological semimetals, whether the band topology can be fruitful for thermoelectric properties or not. And we found Cu2ZnGTU4 to show a unique band structure with complementary topological and thermoelectric properties. The screening parameters that we choose to investigate this class of compounds are band inversion with Dirac-Weyl points, whether they are non-trivial or not, surface states, and most importantly, whether there is a mixture of highly linearized and parabolic bands, because such bands, such coexistence of bands are found to enhance the thermoelectric performance. So along with the topologically non-trivial bands, do we have a mixture of such linearized and parabolic bands, which will be beneficial for thermoelectric? So based on this screening, as I said, this compound was found to be a potential candidate. So this particular quaternary chalcogenide actually crystallized in a tetragonal symmetry with the space group 121. The structure is shown here. It has two formula units leading to 16 atoms in the unit cell. So as I said, this is already experimentally synthesized. So this column shows the experimental lattice constant and volume, and we have optimized theoretically, and these are the theoretically optimized lattice constant. Interestingly, this particular structure preserves time reversal symmetry, but lacks inversion symmetry, which gives a home to realize topological Weyl semimetals. So this is the simulated band structure for this compound. And the different colors in this band structure basically shows the different atom / orbital projected bands. And you can easily notice that the conduction band is predominantly composed of tellurium P orbitals, while the valence bands do have a combination of copper D and tellurium P orbitals. There is an SP band inversion. I had another plot where SP band inversion was shown at gamma point. A search in the entire Brillouin zone. So this is the Brillouin zone on the right-hand side. And, we have done a detailed search in the entire Brillouin zone to find the presence of the nodal points. And we actually found two Weyl points, W plus and W minus, as indicated in this Brillouin zone. You can see these dots. Copper zinc germanium fluoride is a topological semimetal with asymmetric hole and electron dots. You can see that the density of states is not symmetric around the Fermi level, which is also one indication for achieving a good Seebeck coefficients. And as I said, the system preserves time reversal symmetry, but lacks inversion symmetry, enabling the possibility of Weyl points in the band structure. So this is a more closer look at those pair of Weyl points, W plus and W minus. They are reasonably flat in nature. The coordinates of these, the coordinates in the reciprocal space of these Weyl points are here. We have checked the chirality. The chirality are +1 and -1 at the two different points. The band crossing is, of course, slightly above the Fermi level. As you can see, the Fermi level is below. This is just to show a zoomed-in view about this band crossing points. We have also simulated the Berry curvature around these Weyl points, and you can see that the Berry curvature around +1 chirality shows a source nature, while along -1 it's a sink nature. The surface bands, which is on the right-hand side, is projected along the 100 surface. And it clearly shows two Weyl points, W plus and W minus around the gamma point, as we have shown in the bulk band structure. Now, going beyond, so it is, established that this material is a topological Weyl semi-metal. As I said, that is it possible to have another quantum phenomena which coexist in the same material? So thermoelectrics is one of the avenue that we have explored, as you know that this is also a very important area in the renewable energy side, because it converts waste heat to electricity. There has been several source of waste heat, such as thermal power plant, nuclear power plant, vehicles, incinerators, glasses, aluminum factories. And in all these factories, there are huge amount of waste heat that is created. The question is, can we convert these energy into electricity? And there has been tremendous effort towards this direction. And the current status is that we are able to only convert 34% of these energy to electricity. There are still efforts going on to increase the efficiency. And one of the problem with this conversion is that these thermoelectric efficiency depends on a figure of merit, ZT, which depends on several electronic transport properties like Seebeck coefficient, S, the electrical conductivity, sigma, and the thermal conductivity, which involves the electronic contribution, the lattice contribution, and the bipolar contribution. And if you look at a cartoon diagram, which is in the middle, you can see that as we increase the carrier concentration, there is a strong competition between these quantities, which means one is increasing, the other decreases, and hence there is an optimal value that one has to choose. For example, if I increase the carrier concentration, the conductivity increases, but the Seebeck coefficient alpha decreases. If I look at the thermal conductivity usually has an increasing nature, unless there is a bipolar component. So these electronic transports are very intimately tied to each other, and hence an optimization of these quantities are very much required in order to achieve a high figure of merit, CT. So in the application, these are basically used as a P-type and N-type semiconductors, which are connected to calculate the Carnot efficiency, eta, where here this Tc and Th are the temperature of cold and the hot junction, and it uses Zt, the figure of merit, and hence Zt is one of the quantity which people usually work on to enhance the problem. Now, as I said, because the transport properties are very crucial for these, for achieving enhanced thermoelectric efficiency, and which is intimately connected to the band topology, there has been several strategies to enhance thermoelectric performance. The very ancient band topology that people used to work with is which consists of either a light band or a heavy band in the band structure. But the problem with this is that if you have a light band, it will give you low resistivity, high mobility, but then small Seebeck coefficient. So the rho and the S are counterproductive. If you have a heavy band, it is the other way around. You will get a high resistivity, means low conductivity, and large Seebeck coefficients. So there are some strategy based on band convergence, which involves aligning a number of light bands near the Fermi level, which actually improve the thermoelectric efficiency because of the high band degeneracy. Now, in topological semi-metal case, such as Weyl or Dirac materials, these offers a perfect combination of light and heavy bands, which means can we have featured bands, which gives rise to the topological bands, topologically non-trivial bands, And at the same time, if we can have a regular band, which is parabolic in nature and usually more flatter. So if one can have a combination of these two, it will help to maximize the conductivity and at the same time the Seebeck coefficient, which will give you a high power factor S square sigma as required in this numerator. So if I come back to the band structure that I had shown, you can see that this compound indeed has a band structure which has a topologically non-trivial semi-metal band, which is more linear and light in terms of effective mass. But it also has a parabolic band, which is more flatter. And hence, this actually is a combination that we are talking about here. That topologically non-trivial band, which is light, and a regular band, which is more heavier. So this gave us a hint that this may be a good candidate to explore the thermoelectric properties of these. So the band convergence in this case is what we are expecting. So going forward, we have used the semi-classical Boltzmann transport theory to calculate the electronic transport for these compounds. So this is the Seebeck coefficient, then the electrical conductivity, the electronic contribution to the thermal conductivity. By the way, this also includes the bipolar thermal conductivity, and eventually the figure of merit. All these are plotted as a function of the chemical potential, and the carrier concentration N is correspondingly calculated, which are on the top scale. So if you look at the Seebeck coefficient as a function of carrier concentration, so by the way, these calculations are done by using a rigid band approximation, which means we consider to move the Fermi level up or down without considering any change in the band topology. So although these are like a doping concentration, but the assumption is that with the doping, the band topology remains intact. It is only the Fermi level which moves up and down. And if you look at the Seebeck coefficient, the mu less than 0 is the p-type regime, and mu greater than 0 is the n-type regime. The value of Seebeck coefficient is not as high as the state-of-the-art thermoelectric materials. These are reasonably high as such. However, the electrical conductivity is significantly high, and is much higher than even the state-of-the-art thermoelectric materials, which helps to enhance the power factor S square sigma. The electrical conductivity is also in a reasonable range, in the sense that these are also high, and which is expected because the electrical conductivity is also high. And if you calculate the figure of merit ZT, what you get is in the p-type regime, you get a maximum chemical potential of the order of 0.23, and in the n-type regime, you get something like 0.15 or so, which for a pristine compound is not a bad number, because one can also employ further doping and pressure and other studies to enhance this, which is the usual way to enhance the figure of merit. This is basically the temperature dependence of the same compounds, of the same P and T n-type region. So S square sigma, which is the power factor, and the figure of merit at a particular concentration where the ZT is found to be maximum. So at this concentration. And you can see that a figure of merit as large as 0.23 or something like that for p-type, and 0.15 for n-type, which is reasonably high enough for a pristine compound. This is just the in-plane and the out-of-plane transport. So the red line is the out-of-plane component of the Seebeck and conductivity tensor, as well as the electrical conductivity, and black line is the in-plane. And you can see that the out of plane Seebeck is much larger as compared to the in plane because of the number of the bands crossing the Fermi level along those lines. And the power factor is also reasonably high in the in plane and out of plane. This is just to show how the in plane and out of plane contributions are different. The conductivity does not change much, but the Seebeck coefficients are different. To be more precise, conventionally these transport calculations are done in the community using constant relaxation time approximation, which is usually taken to be 10 femtoseconds in conventional semiconductors or heavily doped semiconductors. However, these calculations are done using a variable relaxation time. So we have actually calculated the relaxation time considering two types of scattering: deformation, acoustic deformation potential, and the polar optical phonon scattering. And you can see that the order of magnitude of the electron and hole relaxation time is mostly comparable. Definitely tau is much larger in this case as compared to heavily doped semiconductors, which lies of the order of 10 to 100 femtoseconds or so. And this is because this is a semi-metal and the impurity scattering is weak, is expected to be weak here, and hence very high relaxation time. There is another aspect to this particular material, which arises from the phonons. And more recently, there has been several studies which talks about topological phonon properties. So this is one aspect that we have also studied recently, and these are some of the preliminary results. We're still trying to understand it better, but some of the preliminary results that we have got are quite interesting, and hence I thought to show. So this is the full phonon dispersion, and of course, as you can see, there is no imaginary phonon frequencies indicating dynamical stability. There are high interaction between the acoustic and the optical phonon branches, which hints towards the possibility of low lattice time conductivity. Interestingly, several crossing points are observed in both acoustic and optical phonon bands. You can see, although it's pretty busy dispersion, but if you closely look at certain frequency ranges, you can see that there are several crossing points, which enables the possibility of topological phononic features, such as zero-dimensional Dirac-Weyl points, one-dimensional nodal line, etc. So just to give you a brief...
just reminder, 5 more minutes.
Yeah, I'm almost there.
Sure.
So recently, as I said, there are topological concepts that are extended beyond fermions, and it extended to phonons, photons, magnons, etc. This novel topological phonon concept provides new degrees of freedom to control and manipulate thermal transport. Although this is a pretty young field, but it can actually give us a good platform to control the thermal properties. So there are various phononic topological features which people have proposed, such as Dirac-Weyl phonons, double-Weyl phonons, nodal line phonons, nodal loop, nodal chain, nodal surfaces. A few systems are actually experimentally verified as well, like either cyanide, double-Weyl phonons. As far as the application goes, nothing much has been concretely proposed, but it can be useful in dissipation-less phonon waveguides and phonon diode. And as I said, topologically protected band crosses can influence the thermal transport. So we have chosen certain frequency range and tried to analyze the different topological nodal points. So if I look at the frequency along Z gamma Z direction, there are a couple of nodal points which are observed at around the same frequency range, which enable us to draw a nodal line or nodal loop. Corresponding surface states on 100 surface confirm a drumhead-like geometry, which confirms the nodal loop behavior. The surface R on KXKY plane also indicates a nodal loop kind of behavior. And of course, the finite Berry curvature shows a clear loop geometry centered around the gamma band. Because the phonon dispersion is very ubiquitous and busy, there are several frequency ranges one can find and cross-check the topological phonon crossings, topological phonon behaviors. And these are some of those phonon frequency range where there are nodal points, there are nodal loops, and each of these show finite Berry curvature. We have also observed certain nodal chain behavior, which arises mainly from the overlapping of two or more nodal loops. So you can see in the Brillouin zone, if there are two nodal loops which overlap each other, there is a nodal chain that one can construct. Such nodal chain feature is also reported in electronic band structure in the past. We have found nodal chain along few of the high symmetry lines like P and P1, gamma, Z, sigma 1. Still, we are in the process of understanding these topological phonon behavior better. We have also calculated the lattice thermal conductivity because this is a quantity which is required to evaluate the thermoelectric performance. So this is the lattice thermal conductivity for this compound calculated using a Debye-Holloway model. You can see that the lattice thermal conductivity is reasonably small and hence is beneficial for the thermoelectric figure of merit because the lattice thermal conductivity falls in the denominator of the expression. And the low value of lattice thermal conductivity is possibly due to the strong spin-orbit coupling and highly interacting acoustic and optical phonon branches. So concluding remarks is that like CU2 ZnG24 is a classic example of composite quantum material exhibiting three complementary properties: the topological electronic Weyl semimetals. The coexistence of light and heavy bands gives rise to a high thermoelectric figure of merit. The phonon spectra show multiple topological nodal points, nodal line, and nodal chains. I would like to acknowledge HPC supercomputing facility at IIT Bombay, where some of these calculations are done. DST, SARB, Core Research Grant and Matrix for financial support, and Ames Laboratory. Thank you.
Thank you, Aftab, for a very interesting talk. The floor is now open for questions. So people can raise hands or write in the chat box. Okay, let me then get started. I have a very sort of simple question. I mean, I'm from more of a model Hamiltonian community. So if I'm were to, sort of get the essence of maximizing the figure of merit and write down a model Hamiltonian, light and heavy bands perhaps are easy to make in a model Hamiltonian, but I mean, what would be the bare bone essentials to control the figure of merit?
Okay, so, usually either a very light band, which means low effective mass, or a very heavy band, which means high effective mass alone is not sufficient to get a good figure of merit because it will enhance one quantity but compromise the other. For example, it can increase the Seebeck coefficient, but it will simultaneously also decrease the conductivity.
Yeah, so I was perhaps wondering, I mean, what is the control knob, if you will? I mean, what term I should add, if you will?
Yeah. So the control can have a set of bands aligned near the Fermi level, which can enhance my band degeneration as well as the carrier concentration. So you remember that the Seebeck coefficient and conductivity both depend on the carrier concentration, right? And the band degeneracy plays a role there. Yes. So is it possible we have a set of light and heavy bands aligned near Fermi level so that some of them can help me to enhance Seebeck coefficient and at the same time the others help to enhance the conductivity. And that is precisely done in the band convergence figure, which I showed there. So they have actually showed that if I have a set of bands near Fermi level,
Yes.
yeah, so some of them can help to enhance the effect, the mass, and hence the Seebeck. And also band degeneracy plays a more crucial role here, because N is one of the controlling factor also. Conductivity is directly proportional to N, but inversely proportional to mass in an empirical sense.
Yeah.
Right?
Yeah.
So if I can imagine a situation where my carrier concentration is dominating over the mass, enhancement, then I will win.
Yeah.
Right?
I mean, let me see if there is a question. I'll probably ask you at some point else. So it's a very interesting topic. There is already a question. So Vishal, please go ahead.
Hello. Yes, sir. So, sir, my question is that in surface states, sir, you showed the Weyl points, sir. So, sir, how do we know that this in surface state, how to recognize this is the Weyl point, sir? So, in band structure, it is, sir, simple crossing. But in surface states, actually, I don't understand how. Yeah, this is the Weyl point. So,
yeah, definitely. So when you simulate the surface states,
yes, sir.
There is a way you can separate out the bulk contribution and the surface contribution in it.
So, sir, this one blue one is.
So the red ones are the surface states here, which is quite sharp, as you can see. But then there are also places which are either very light red or blue colored.
Yes, sir.
So the blues are basically behind
bulk.
Yes. And so although I have just shown it here right away, but if you subtract all the surface contribution from this graph, you will only see that there are 2 points which actually crosses, one at W plus, one at W minus.
Okay.
That can only give you a bulk type of contribution.
Okay, sir. So, thank you, sir.
Okay, I don't see any other.
I have a quick question. After, thanks for the nice talk. This is SETI. Yeah. So, what would be the symmetries protecting topological phonons in your case? Maybe you may have mentioned, but I missed it.
Correct. Yeah. So, in this case, although the time reversal symmetry is, respected, while the inversion symmetry is broken, a Weyl point was expected. However, what we have got are these nodal points kind of behavior, as you can see here, right? So we, as I was telling, that we are still trying to look at it more closely, because there is such a huge phonon frequency range.
Okay.
There is a possibility that at some phonon frequency range, there are also topological Weyl Weyl points. We have not yet located that.
Okay.
What we have got is a bunch of nodal points which actually fall at or near the same frequency range, and hence there is a possibility of nodal line. These are very clearly observed here.
Okay.
But, yeah. So there are symmetry imposed phonon topology as well.
Okay, thanks.
Yeah, after nice talk. So I was just wondering how the Berry curvature, I mean, if you have Weyl here, you must be talking about the Weyl as well here, for the phonon case also.
In the phonon case?
Yeah.
Yeah, actually, we have not got any Weyl points as of now. We have tried to look at several ranges. These points are either nodal line kind of behavior or nodal loop. There is no chirality that we got plus or minus for this respective, crossing points. But I'm pretty sure there will be some frequency range where you will have a band crossing which are of Weyl nature.
Yeah, sure. There are other matrix I was just wondering whether your thermal conductivity
Uh-huh.
can be presented in terms of the chirality, Berry curvature, just like in the electronic system we do that, right?
You're talking about anomalous Hall conductivity?
Yeah.
Electronic structure?
Yeah.
Yeah. So there are that anomalous phonon Hall effect aspect also in these. The thermal conductivity that I showed is a lattice thermal conductivity. So this is like the usual electrical resistivity or electrical conductivity that we calculate in electronic excitation. The anomalous Hall transport still needs to be looked at. But there are those aspects to these topological phononic band crossing as well. We have not yet looked at them so far.
Okay, maybe we should move on. Oh, after just, we have to formally take your permission that you're okay with we recording your talk.
Yeah, that is okay. That is fine.
Okay, so Manoranjan, you are done, is it?
I'm done.
Okay. So okay, let's thank Aftab for a very interesting talk. Let's move on to the next one. Thanks, Aftab.
Thank you.
Argoda, maybe you can share your screen.
Happening. Can you hear me?
Yes, I can hear you.
Yeah. Now I can share because it was locked by somebody.
The other person had to unshare before you could.
Right. So let me share. Let me try to share. Entire screen, share. Why is it not coming? Just a second.
Sure. I think this is the last talk, so we have some time.
You have to share the screen, right?
This one I want to share.
This one.
Okay, it's coming now. Yeah. Can you see it now?
Yes, it's visible.
Yeah. Okay. So shall I start?
I think it's better to go to the full screen mode. It's still showing in the window. So if there is,
let me try.
If you want to see, then you will have to go there. Then you both can't be in same place. So, like
just a while. I'm just too old-fashioned to.
This one, right?
Yeah.
What is that?
They want the full screen.
Okay, they want the full screen. Since we're using PDF, right? We're not using
I should have
the full screen, the third from the last.
Yeah, I got it. Yeah. Is it okay?
Yeah, it's fine. It's fine.
Okay.
If you want to zoom, just Control and plus. Okay, it will be zoomed.
Okay. Thank you, Anamitra.
Yeah. So let me introduce you, Argoda, to the audience. Of course, you don't require introduction to this audience. It's our country. So Professor Argo Tarafdar is a faculty from IIT Kharagpur, and he is going to talk about topological signatures in LOS2 interface. So Argoda, please, I will remind you 5 minutes before the end of it.
Okay, thank you so much. Okay. Yeah, this is I'm really sorry that I could not attend much of this conference because this is our it's a very complicated time at teaching institutes because we are I don't even know which mode we are teaching, how we are teaching, and this is also the mid-semester time and the exam time. So life is too complicated. Really, we do not know whether we are existing really or virtually at some points. Nevertheless, I'm very sorry that I could not attend much of it. And what I will do is that I will introduce you to a subject which is which became very important around 2005 or so. And then, of course, it's still continuing, but it has survived the onslaught of topology by having its own topology in some sense. And those are things I will discuss a bit. There are many more things that have come up in the interfaces, particularly the oxide interfaces. And it started with just one oxide interface. Now there are more than 100. And so I will just give you a glimpse of what is interesting about these systems, And much of what we have done is already in the form of publications. So that's really not a, I don't have to really emphasize on those. Anybody can look up. The first interface was this LAO-STO interface, and this came out in 2004. And then these are two band insulators actually. Some people try to convince us that this is the Mott insulator SRTiO3, but it's a D0 configuration. So even if there is a Mottness, that is very little. But nevertheless, these are wide bandgap semiconductors, insulators. And when they were put together, they showed an interface which became metallic. So that is the interest in this, and that and as you know, oxides are systems where you can play around. Therefore, once such oxide interface has formed and it's a two-dimensional interface, so people became very excited. So this is the first result that this is I think the second or third result that came out of this group in Germany from Manhart. And what they found is that this is you need at least 4 layers on top to have this conductive, this insulated to metal transition. So it's a layer driven. A number of layers decide when you will have a insulating phase at the interface. So that turns out to be 4 in these systems. This is of course not a generic property of all oxides. The different oxides have different properties. So, but this one was really remarkable in this case. Now, as I said, there are very, very different kind of interfaces possible. I will come back to this one. This is a polar non-polar interface, where one side has polarity, and the other side is non-polar. Whereas now you can get all kinds of interfaces. So as you see, there are these 3 possibilities now. All of them have been discovered, and all of them show a 2-dimensional electron gas at the interface. So the mechanisms for each of them could well be different, or there may be an underlying mechanism which is common to all that we still do not know. But nevertheless, there is this 2-dimensional electron gas at the interface. Now, this was as I said, this was the first one, and this is a polar. For example, LaLO3 is a polar material, and SRTiO3 is non-polar. So you see, the polar material has this kind of a charge structure, +1 -1 +1 -1 in some units, and then therefore the density has this profile. Correspondingly, the potential is a runaway potential. So that potential has to be arrested. This potential going very large, and that is how the system reacts to stop that runaway potential by transferring some charges and basically making a capacitor out of it. So these are all well known. I am not getting into the details, but this is just setting the stage. So there are many kind of 2 terminations possible, so on and so forth. Okay. So the interest in these systems further increased when one found that there is superconductivity at this interface layer, electron gas, and this is really surprising because, first of all, 2D superconductivity is very rare. You don't expect it to happen. If it happens, it will be of Kosterlitz-Thouless type. That's the expectation. And then, of course, this system, as I will show, has a magnetic, ferromagnetic ground state. I don't know if it is a ground state, but if you measure magnetism, you will get a magnetic structure. And so, therefore, superconductivity to appear in this case is really very surprising. There are further surprises that people realized immediately that if the interface has to be superconducting, because of the lack of inversion symmetry at the interface, there is a strong Rashba coupling. And therefore, the superconductivity that you are getting may not be the garden variety SO superconductivity. I think Ovik Bid's group in India has done a lot of work on these 2D superconductors, and we have been fortunate to collaborate with them in 2 papers. And what we found is that indeed there is a strong signature of 2D superconductivity of Koszalej-Thouless type superconductivity in this system, both in noise and in magnetic field responses. So this is the control of transport in this system. These systems are bottom gated, and for reasons which I will not get into here, but experimentalists know it much better, that you have to bottom gate these systems, and then you get this wonderful phase diagram where you can actually have a superconductor to an insulator transition. So this was the experiment. This is what people tried to fit to show that there is a Koszalej-Thouless kind of transition. And this is the phase diagram. As you can see that the Z nu bar, this exponent, becoming 2/3 is actually a signature of a BKT kind of transition. And people actually fitted it to that close to that value. And this there is a quantum critical point. Expectedly, there is a quantum critical point somewhere here at low certain gate. You have to maintain the gate voltage at a certain region so that you get superconductivity, and then lower the temperature, you get this quantum critical point. The resistivity, for example, above the transition has this kind of a behavior, which is also a signature of quantum criticality. So not only quantum criticality, but BKT kind of transition. Now, as I said, that there is a magnetism in this system, and magnetism goes the magnetic. If you want to call it a TC, you can call it, but the magnetism turns out to be very fragmented. But then there is a net magnetic moment that you can see, and the magnetic moment is fairly large compared to the density of electrons in these systems, and that is about 0.3 to 0.4 Bohr magneton, and therefore, and that vanishes at around 200 degree Kelvin, between 200 to 50 degree Kelvin. So therefore, there is a large magnetic region in which that superconductivity occurred. And if you look at this SQUID data, scanning SQUID magnetometry image, then you will see that there are patches of superconductivity and ferromagnetic regions. Whether they overlap with each other or not is not very clear, but there is now, at least there is a strong belief that this is basically phase separated. I'll come back to it if I get time. The other thing is that these magnetic moments are extremely anisotropic in the sense that they only live on the plane. There is no magnetic moment in the Z direction. So that is expected, of course, because these are planar structures, and moments are mostly, I mean, the band from which the moments come are in the dxy bands. So the geometry is expected to be in the plane. Okay, so this is the basic band structure of these systems. This is the kind of things that the model builders start from. As Anamitra was saying, that we are model people, and for us, such a clean picture is really quite reassuring. So what happens here is that you can, in the Ti3 plus structure, you can have a moment at this dxy orbital. This has to be dxy, which is pretty clear because that is the other directions are non-dispersive. The z direction is non-dispersive. So that's what is corroborated by band structures as well. And then you can see that the dxy band is close to the Fermi level. So that's where the action is. But it is by no means absolutely clear that you should only work with a single band Hamiltonian, but that's a good starting point. So this is the band structure, and then you can see that whatever small charges you have, the mobile charges are in this region in the dxy orbit. So you can write a model Hamiltonian, and with a single band model. I'll come back to 3-band model if I have time. Then you can, of course, this is the standard Hamiltonian, and you have to add the Rashba. And of course, because there is a superconductivity and magnetism, you add the Zeeman field and the BCS pairing term. Okay, so this is what you will get. This is the chiral basis in which the bands are now diagonal in this basis, and because of the spin orbit coupling, there is a locking of this moment and angular momentum and the spin. So the green ones are, I suppose, spin, and the I think the brownish ones are angular momentum. Nevertheless, what happens is that there is a separation of the two comma point, and the actually Berry curvature shifts to a point P, which is most likely, as far as I remember, is minus hx by alpha. So hx represents the Zeeman field. So that so therefore, if you want to have superconductivity coming out of these two bands, the momentum has to be finite. There has to be a center of mass momentum. It's a finite momentum spin mixing that leads to Cooper pairing here. Now that's what Patrick Lee and company first suggested, that this is an example of a full day Ferrel and Larkin-Ovchinnikov state. And they suggested that this is another example, which is very rare of FFLO state. Nevertheless, we actually went ahead and we did the calculation, the full-blown calculation, for taking into account the fact that the system is intrinsically very disordered. Almost every experimentalist tells you that the interface is extremely disordered. Quite disordered. I mean, people have made very good interfaces now, but even then you cannot avoid atoms diffusing out. So there is an intrinsic disorder, and therefore you have to solve the BDG equation, including the disorder, which we did the simplest possible case. Remember, once you have this kind of a situation where the SOC mixes these bands, you cannot avoid. I mean, your pairing will also have the P wave channel. In this basis, you will have a P wave pairing. So that comes into play now. So we know that normally Anderson's theorem tells us that an S-wave superconductivity is not affected by disorder, whereas in this case it is not an S-wave. It is because of the P-wave mixing. We have to be careful, and we believe that there is a strong influence of disorder on the superconductivity, and that's what is borne out from our calculations true, and of course experimentalists also corroborated to this. So let me not get into the details of these things. As you can see, the order parameter, the gap quickly drops down, but never saturates to never goes down to exactly 0 to up to disorder 6, but it finally goes down. And even at 0 disorder, there is just a lot of fluctuations, and that fluctuations lead to a non-zero gap, even at gap vanishing, regions of vanishing gap at even 0 disorder. And that's kind of interesting. And since magnetism is lurking in the system, you are working inside a magnetic dome, it's interesting to see what happens. In any case, to complete the story of this, we actually also calculate the rho sub S. There is a bit of a difficulty in calculating the rho sub S because you are in a disordered system, and so you have to restore the transitional symmetry by averaging over thousands and thousands of such realizations. And with our kind of computer facility, this turns out to be very difficult. But anyway, this is how the rho sub S behaves, and it goes down to 0 by about disorder 6, strength of disorder 6, where the bandwidth T equal to 1 is the scale. Now the point is that what happens to magnetism? So what happens is kind of interesting, and I will not prolong the story, but the magnetism, it turns out, appears in phase-separated regions, and that's exactly what you see. So this is superconducting. You can see the superconductivity is in regions which are separated from each other. Then there's a ferromagnetic region which is also separated, phase-separated at slightly large disorder. And then if you put these two together, you will see that they actually avoid each other. So that means there is a complete phase separation between superconductivity and magnetism. And that's how superconductivity survives within the magnetic dome. And so it's not a full deferral kind of state. And I think now almost the general belief is that indeed it is a phase separated scenario. Now, as I said, that you have a P wave component to the superconductivity at the interface, there is a lurking possibility that there could be a topological superconductivity, and indeed there is. So, and then if you have a topological superconductivity, then the question is, can you make it a topologically non-trivial superconducting state? Can you stabilize it? And once you can stabilize it, can you follow the Green and I think Green had a suggestion that there is a Nick Reed and Green, I think, that if you have a topological superconductor, then there is a possibility of mediating the Majorana bound states at the edge states, so at the edges. So that's a question that one can now ask. And so therefore we took it up, and at that time, it's about 2012-13, there was a lot of activity going on searching for Majorana bound states in condensed matter systems. And therefore, if you remember, there is one-dimensional semiconductor, superconductor junctions and proximity effects and so on and so forth. People have been trying to get Majorana bound states because, obviously, for quantum computing, these would be very useful, topologically protected states. Therefore, we thought that this is a playground where one can look for MBS, and that's what we did. So to get an MBS, what you have to do is you have to put a field in such a way that what we found out, that if you can put a field in the Z direction in such a way that one of the helicities is out of the Fermi level, you can push it up from the Fermi level, and Fermi level falls in only one helicity, then there you can have a non-trivial topological superconductor. So that's what we actually did. So it has to go, it goes to a gap. So if Hz reaches a critical value, then you can actually go through, your gap vanishes, and then you get into a topologically non-trivial superconducting state. And once you are there, then you try to construct situations where you can have, or at least look for Majorana bound states. In a finite system, that's non-trivial, but we actually went ahead and we looked for it. So most of you know who and what Majorana is. Just like his particle, he himself is quite elusive. Nobody knows what happened to him at the age of 37 or 30. He went away, and there's no trace of him since. But Majorana bound states remained, and Majorana fermions remained an enduring legacy. And in condensed matter, we have hopes of finding it. So these are, of course, as collective states. But nevertheless, people have suggested it for fractional quantum system for filling 5/2, and superfluids in helium-3 for an A phase. And strontium ruthenates also people have suggested it because there is a possibility of a P wave superconductor there. Okay, so how do you do it? As I said, you can tune your field and your Rashba coupling in such a way that you are in this region of the phase diagram, and therefore now you look for it. Now, in a system where you have only one vortex, you can, one of these Majorana bound states, they always come in pairs, and one of them will be at the core, at the gapless region in the core, and the other one will be at the edge. So that's what we actually looked for. And so we created we have a vortex solution here. And now there is a caveat to this, which I must tell you, that the look at the values of Hz. If you convert it into real values, it's very large. So that's actually, I mean, after our paper came out, the first objection came from from Alan MacDonald, and he pointed out in a paper of his. He discussed the solution, and he actually pointed out that Hz values are severely large, and so any laboratory you cannot do it. What you can do, of course, is what our suggestion was, that you can intrinsically generate that magnetic field inside self-consistently. If you can do that, then there is a likelihood that you actually can produce a large magnetic field. So that's the caveat I must tell you about. Nevertheless, if you can believe that that is possible, and we believe that it is not impossible, and so therefore this, and many other people also believe that this is not outrageous, this can indeed happen. Then you can see that there is a region, which is the P region in the phase diagram, where you can have Majorana fermion. So what we did is that we looked for the existence of this bound state at the core of that vortex. So that vortex.
Just remind us, 5 minutes.
Yeah. Okay. Sure. See, I don't have to finish my talk. I mean, wherever I run out of my time, I stop there. Thank you. So this is the low energy spectrum of this. You actually have to look at the spectrum, and you are looking at a zero bias state. So let me just show you the regions. See, this is the region 1, for example. Okay, so let me. Yeah, so the region 1 is the gap region, superconducting gap region, and nothing happens here. You are not supposed to find the zero bias state here. Okay. This region is interesting. This is where your magnetic field is producing a magnetized region, and these are magnetized. As you can see that these will. So this is a better picture. So this, for example, is a as you can see, these two red lines, although they start from 0, but they linearly increase with magnetic field. So therefore, these are magnetized states. These are states that are magnetized. Now the vortex core gets magnetized. Here is the interesting region. This is where you have actually a non-trivial superconductivity, topological superconductivity, and immediately you see that at this point the non-trivial superconductivity sets in, and here the gap, there is a state which is not affected by magnetic field at all, and it's 0 all the way. So this we believe was the Majorana fermion. So then we went ahead and actually looked for it in terms of wave functions and its amplitudes, and we actually located it half a fermion in the central vortex. The edge state is extremely hard to localize edge Majorana because of the amplitude is so small, it's all around here. But that's the story. I mean, at least this one we could look at. And we plotted the tunneling spectrum, the LDOS basically. And as you can see that there is a strong zero bias anomaly at this around here. So this we believe is the signature of Majorana. So we put it up in the archive, and next day we got a mail from Manhart's group saying that Richter in his thesis has actually seen this kind of a spectrum in one of their samples, and they wanted us to compare with the values. We actually did. My student Narayan did it, and then Narayan went there as a postdoc, and he later on wrote a paper comparing this theoretical result with their findings of Richter that is reported in his thesis. So that's an aside story, but it is unresolved still. You can believe it or not, but at least these calculations do show that there is a strong zero bias anomaly, which is experimented with Richter's experiment can be matched to about 60 to 70%, but the weights and all that, but it is still unresolved, as I would say, whether there is really whether they have really seen this Majorana bound state as we have predicted. I mean, they did it before us, in the sense the experiment happened before our prediction, but they had the result. They did not publish it because there was no theoretical support. So once our paper came, they actually later on the Narayan and that Richter and company published a paper. So this is what happens if you put disorder in it. Now, as you can see, the zero bias anomaly very rapidly vanishes. And that's expected that this POF superconductor is, as we showed, is very susceptible to even non-magnetic disorder. So, I mean, this is the comparison from Richter's and ours. This one is Richter's result on the left-hand side, and this is ours. And I mean, you can look up Narayan's paper. Then we went ahead and did a multi-band superconductivity, but I will not discuss it because 3 bands are essential to describe the system at the end, and there are interesting features of that superconductivity there. The thing that is another signature of the topology is a Lifshitz transition, and that was reported experimentally by Joshua et al. And this is the point where they found that there is a Lifshitz transition. Since I don't have time, I will not get into the details. I mean, this is what happens. In this band is the dxy band, and when your Fermi level crosses this, then you see the other. There are 6 bands actually. SOC makes it 6, and the other bands start contributing. And the nature of these other 2 bands is very different from dxy band, and therefore the transport has a strong signature. Should have a strong signature. Unfortunately, it is very difficult to experimentally locate a Lifshitz transition, and they tried from this transport data, from total transport and the heavy heavy electron transport. They tried to separate out and tried to see where does this transition take place. So what we suggested is that we did a calculation. We suggested that it is actually much better to look at. We actually had to do a correlation calculations here using DMFT, but the idea was that look, you cannot look at this heavy hole and heavy electron and light electron transports. It's very difficult to delineate them. Better to look at some transport coefficient, something, because the Fermi surface geometry is dramatically altered by when you cross, and also by interactions. And so what you should look for is something which is this Seebeck coefficient. You see that Seebeck coefficient at the transition has a strong cusp, and this is a better criterion, better diagnostics to look for Lifshitz transition in this system than the transport, just the mere transport, the Hall or conductivity or so on. So I think I will stop here, and I will. And we showed that if you put a strong magnetic field, you can actually separate out 3 such cusps, 3 Lifshitz transitions very clearly, and that should be the best diagnostic for this. So let me stop here, and Anamitra, I'm done.
Thank you, Arbuda, for a very interesting talk. Very interesting talk, and now the floor is open for questions. So please either raise your hands or you can write in the chat box. Maybe let me then ask a question in the while people can formulate their own. So I had just when we were looking at the very beginning of the LAST interface, so we were so if I'm correct, you said that for the phase separation to occur, you needed disorder to be present in the system. Is that a correct statement?
Well, disorder enhances it, certainly.
Okay. No,
Even at weak disorders, you can have regions of phase separations. Yes.
I think. No, I was my question more so was in the even in a sort of ideal clean interface, there could be, because there is charge reconstruction across the.
Absolutely, absolutely.
There could be phase separation naturally.
Yeah, we had another paper which is not topology, so I did not show it here. We actually showed that there's a charge clustering. There's a vacancy clustering that happens, and what you are saying is exactly true. I mean, that's exactly what happens.
Okay. Okay.
Yeah.
Okay. Thank you. There is a question from the host, so please go ahead.
Argoda, nice talk. My first question is that in the disorder system, I mean the phase separated limit, what is the coherence length or the size of the superconducting?
Extremely good question. Very, very good question. And the answer to it is there are two parts to the answer. One is that you have been saying that you will visit us, but you have not. So this is a place where you should promise to visit us in front of others. And the second part of the question, the answer is that it is very hard to find out because the coherence length varies from region to region. And there is actually a paper from Annette's group where they find that the coherence length could be from 10⁻⁶ to 2 of the order of microns. So from 10⁻³ micron to micron range, it can vary.
Yeah. Okay.
For us, it was difficult to calculate because you see, it's a finite size system. So particularly in the clean limits, it's hard to calculate those things.
Yeah, I mean that's okay. The second question is Majorana system. So in the Majorana system, it's a 2D system. So you have the Majorana around the edge of your.
Correct. One of the Majorana is around the edge.
So once you put the disorder, because you're also seeing the disorder.
Correct.
So what exactly happens to the Majorana? Still it's there?
So the Majorana will immediately become an electron. I mean, that is what. Two Majoranas will just become an electron because they are coupled. After all, they are, they are topologically coupled. Quantum mechanics couples them. So if you put a disorder, the Majorana state vanishes basically. That's what we showed I showed in the last picture that see, I cannot really tell you exactly how it happens because it's all quantum mechanics. I don't have a physical picture of it. But what we saw is that the Majorana, that bound state, that signature vanishes very quickly.
I see. But ideally, it should be protected, right? I mean, like unless the unless
protected.
Impurity is the boundary.
Right. So that's what I'm saying. Once you put an impurity, then what happens physically, I do not know. But I expect that the Majorana should go, and it went. I mean, it vanishes.
Okay. Thank you very much.
Okay, I don't see any other raised hands. Anybody wants to ask, please go ahead.
Yeah, Anamitra, you should also visit us. I mean,
sure. I mean, no, we have
now that it is, now that we are out of it, we should all meet.
Sure. I'll plan a visit.
Yeah. I think there are no more questions.
There are no more questions. So
you are recording, so I give my consent also.
Yeah, okay, sure. Thanks for that. So with that, let's thank Professor Argo Tarokdar for very interesting talk, and we close this session.
Yeah.
So we'll resume at 17:45.
Thanks.
Thanks
for sharing Professor.
Thank you.
So now I think we will take a break, a coffee break, something like that, for half an hour. So we will reconvene at 5:45. Yeah.
Nitesh? Nitesh, are you there? Bahadur? Professor Bahadur Singh? Professor Nitesh?
Sir, he is not here.
Is not here. Nitesh is logged in. What I would recommend, can you just request everyone just before the session to sort of switch on their video and take the like a snapshot of each of the window?
Just at last of the conference
no, I mean just before this session you can do that.
for this session. Okay.
Yeah, you request everyone to have switch on the video and then you can.
Okay, sir.
Professor Nitesh Kumar, are you there? Professor Bahadur, he is also not there.
I would like to request all the participants to switch on their video so that we can take a snapshot.
I think you have to say this after this talk, because now.
Are we doing now or afterwards? It's not here right now. Not right now? After this talk, we will do that. Okay.
Professor Nitesh, are you there? Professor Bahadur Singh? Professor Bahadur Singh, do you want to check your talks, I mean, slides?
Manoranjan, he is not there. Although I see Nitesh, I don't see him.
Yeah, that's our first speaker.
Maybe you call him or do something.
Yeah, I don't have his number.
Then you switch.
Kalavaranda, do you have his mobile number? Can you please call him?
I'm calling, yeah.
Yeah, he joined. Yeah. Professor Bahadur Singh, can you check your hi. Please check your slides. Actually, it's almost time. So now
Okay. Let me. But where is?
So shall we start?
Okay. Why is it opening? Okay. So is my screen visible?
It's blank actually. It's visible. Something is there, but it's sort of blank.
Let me stop. Then again, I'll try.
Please. Yeah.
It's going away, I think. It's an empty screen. I think there is some display.
Now is it visible? I'm not, because here from me it seems I have shared my screen.
You log in again.
Okay.
Yeah, it seems that you are going to give the Blackboard talk. That's what it looked like.
It seems Zoom doesn't like me.
Yeah, it's okay. You please log in again.
Actually, he used the Apple. No? So
Yeah, sometimes that creates problem.
Usually it's easy. It goes away. It comes and then it goes away.
Yeah.
Why don't you change slides and see?
That's muted.
Yeah, it is coming. Yeah, that's very good. Yeah. So, yeah, this is your collaborator list. We can see. Again, it has gone. Professor Bahadur Singh, are you there?
Yeah, it's there, but
yeah, it has come now. Yeah.
Okay. Yeah, I'm really sorry. I don't know what happened.
No problem. No
I was
problem.
here. Yes.
No problem. So shall we start now? Yeah, welcome to the last session of this conference. And today our first speaker is Professor Bahadur Singh from TIFR. And he's going to talk about the tunable Dirac and Weyl fermion states and SRIN2 AS2 class of gentle materials. Professor Bahadur Singh, please go ahead.
Thank you. Thank you, Professor Manoranjan. And sorry about this hurdle. I thought it will be much easier, but it seems Zoom has moved. Okay. Before I start, good evening, everyone. I am Bahadur Singh from Tata Institute of Fundamental Research. I am leading quantum material design laboratory in the Department of Condensed Matter Physics and Material Science. So before I start my talk, let me thank the organizer for putting this nice event together and having us here. We earlier planned to join physically, and I see Professor Kalubran Maiti is in the audience. But yeah. So before let me start by saying any high scientific breakthrough is enabled only when we have access to high quality material with substantial novel physics. In this regard, first principle band theory paradigm has actually played a leading role in predicting many topological quantum material, characterizing their silent characteristics, as well as guiding or providing a sharpened interpretation of experimental results looking at the energy and length scale, usually not accessible in experiments. I have been involved in many of the initial topological material prediction, which you can find on our webpage, and we are actively working on various other fascinating materials, not only topological material, with where considering the whole realm of quantum material. In today's talk, I'm specifically talking about the tunable, how to realize tunable Dirac and Weyl fermion states with reference to one material class, that is strontium, indium, arsenic class of gentle materials. So now, okay, I hope my slides are moving, right?
Yeah, it is moving. It is
Okay.
moving.
So yeah, so this work, although I'm fortunate to have collaborations around the world, in extensive collaboration in-house. You have heard talk of Professor Kalu Maiti and also Professor Tamizabel in last 2 days. So in this work, I have worked extensively with the Professor Amit Agarwal's group at IIT Kanpur, and analytical support is provided by Professor Shiming at National Satyan Sen University. And the ARPES work I will be going to talk is provided by Professor Madhav Mukherjee's work. So here is the brief outline of my talk. Although I think there are substantial introductory sessions of topological materials, but in order to just facilitate my earlier discussions, I will just briefly introduce the topology in electronic states, where we describe how we calculate the topological invariant with reference to first principle calculations, and we look for the measurable quantities which can be verified in experiments such as surface states. In second part, I will actually move our my idea or our idea is to look for a tunable topological states. And in particular, we will consider how magnetic shape the topological states and describe various designing strategy and with reference to another first non-collinear ferromagnetic Weyl semimetal in cerium aluminum silicon class of materials. And then in third part, I will discuss this strontium indium and finally summarize my results. So now topology has already emerged as one of the fundamental fundamental principle for organizing the quantum matter. So one can put it under a various other degree of freedom and how they interact in a bigger umbrella of quantum material. So theme of our research is basically how topology couples with symmetry and magnetism, which I'm going to cover in this one. But in more broadly, we are looking how topology coupled with various orders, spin, charge, lattice, or orbital. So what the quantum material is generally an umbrella term, which brings many branches under same umbrella, which the theme is actually various interacting degree of freedom. So its emergence starts around 1980s with two parallel discoveries. One is quantum Hall physics, which use the quantum topology or the geometry of the wave function. And the other is high TC superconductivity, which take into account the strong electron interaction. These fields grows over the year, and now we are sitting at present state where we are looking for various robust material that can be subsequently used in the future technologies. Okay, so now being in a condensed matter physics department at TFR, I used to set up a new theme here with all topological condensed matter physics and material science, where we start to look over all the states which can be characterized under the topological lens. Okay, so obviously when we start looking for a material perspective, then only low energy models are not enough, and we have to go beyond that, and one has to consider the material specific computations. In this realm, we are doing the first principle calculation, mainly focused on the density functional theory. Although few people working in the field, we know, although they are very good at some level, but if you want to include more atoms or more deeper insight into the case space, the computational cost increases substantially. So in order to reduce, what we are trying to use is we are using a different methodology, doing the first principle calculations here and then generating material specific tide winding and K dot P model. So we just can reduce this scheme, and now here in this modeling, we can use any interaction, or we can calculate Berry curvature, and we have a more room for the user development, which we are doing in parallel to using the first principle computation. And we have seen this three-way process, although looks a little lengthy, but it is it's very much useful in comparing with various experimental results, either RPRESS or STM, STS or transport experiments. Okay, so now let's see how within a first principle, how we can calculate, say a system is topological or not, with a famous example of bismuth selenide. If we, let me see why it's not, yeah, if we see here, just looking over a simple ionic picture, we have bismuth with 6p3 orbitals and selenium with 4p4. And in this, we just do a simple ionic model kind of things without doing any calculation. We can clearly see selenium has a more tendency to gain electron and to lie in the valence band. And similarly, this bismuth P loses and can goes to conduction band. And so in a very simple model, if we just separate this lattice apart, then we can see like this is the normal ordering which we are expecting. As we start moving to crystal materials limit, they form band, but still valence is composed of selenium and conduction is composed of the bismuth atoms. However, if we conclude a spin orbit coupling, something strange happens. This bismuth goes to valence region, whereas conduction states goes to conduction region. So this is a non-trivial reason which we are looking. Again, this band inversion obviously is one of the pinpointing criteria for topological states, but it's not enough. On the other sense, if we just start looking over its wave function, for example, here we will strictly notice a singularity in selenium wave function. And if we start calculating associated Weyl curvature or Weyl curvature fields or spin Weyl curvatures, this comes out to be non-negligible. So based on that criteria, one can define various topological states. But this band inversion, which shows the change in topology, of one of the essential characteristics. However, in order to really pinpoint a topological state, one has to look for invariants, and we know like why now, depending on how symmetry, quantum geometry, and wave function couples together give rise to many different aspects. So let's consider one example of topological insulator where we calculate the Z2 invariant. So although this Z2 invariant can be calculated by more advanced approaches such as linear charge center or the using symmetry indicator, which recently proposed. But if we consider from first principle framework, if we have inversion symmetry, what we have to look is just look at the count the inversion eigenvalue of the occupied state at certain momentum points, such as gamma 1, gamma 2, gamma 3 in 2 dimensions, which has time reversal invariant momentum, and plug that value of inversion eigenvalue to this formula, it will nicely comes out to be 0 or 1, where 0 remains trivial or non-trivial, and 1 is non-trivial. In 3 dimensions, these numbers can go to further. We have a set of 4 numbers, where first is the strong index, which take into account all the 8 time reversal invariant point in 3D, and then the others are weak invariants that define the John boundary planes. Just from here, using the information of the bulk band structure, we can determine the numbers. And as a earlier speaker also introduced, a topological quantum chemistry or the briefly symmetry indicators that can use now in parallel to adiabatic continuity to predict the states is a topological or non-topological. For a theoretical point of view, this looks very good, but from experiments, they need something which is a measurable quantities. However, these numbers are not measurable for experiments, and they have to, and then for that, we have to look another, and there's the one answer provided by Weyl as correspondence. So the surface state, which actually are the interface between a non-trivial state and the trivial vacuum, are the hallmarks of any topological states. So basically, gapless surface state is hallmark of a topological state, and which is also a measurable quantity. Okay, now by combining these various methods of bulk band calculation with the surface states and their associated properties, a large variety of topological states as well as material have been predicted, and I have been involved many of these early prediction, such as the Weyl semimetal in lanthanum, aluminium, germanium class of material or topological triple point semimetal, Dirac semimetal, combining to topological insulator or crystalline insulator. So all these materials gives a hope in this, as long as our symmetries are protected, the state stays robust, so we can have a backscattering free transport, fast and low power electronics can be utilized for low power electronic and spintronic devices. However, in these states, the mostly earlier realized states are non-magnetic materials, for their functional tuning is strictly lacking. Okay, so in order to see how to track this problem, we start working around 15/16 to how to realize a tunable topological state. And the answer, one can look for a topological semimetals or Weyl semimetal or Dirac semimetal. And the one fascinating family emerges as the Huesler families, which having thousands of materials. So if we can change, this is a simple cubic crystal structure. If we just replace, face centered cubic, if we just replace the various red, green, and blue atom, we can have a substantial materials tunability. Moreover, it has various mirror planes, and those mirror planes are in fact sensitive to magnetization. So depending on the magnetic easy axis, we can tune the particular topological states. This is just example giving on the case of cobalt, this titanium, germanium, GE, and then here it has a 3 nodal line in its spin channel. As we switch on the spin orbit coupling with the magnetization along 001 direction, all the nodal lines which are not on the mirror planes are gap out to realize the Weyl nodal fermions, whereas this particular nodal line lying on Kz is equal to 0 plane is stay robust. So now by just tuning the magnetization this direction by external magnetic field, one can go from one state to other tunable topological states. However, just this is a more like a cubic system. So working again have a many disordered and all those there is a more challenges. So based on that, we start looking how to play with the mirror eigenvalues or how mirror eigenvalues in the system, and then proposed a more robust or the various other nodal line semimetals. Or if we consider in a magnetic system, we don't have a time reversal symmetry. So states are itself singly degenerate, and if 2 singly degenerate states comes together and then combine at certain mirror planes, they form a nodal line. So if these 2 mirror planes, which are represented by this and then this blue one, if they are lying along different directions, then we can have a conventional ring which is separated. Or one can also tune these rings to lie between each other, and then we can have a link which is Hopf link. And now we have realized these particular states for cobalt, manganese, gallium state of system. And one can also have an outer nodal chain or inner nodal chain. And depending on the various combining of this mirror eigenvalue or mirror eigenvalue of the states, one can actually design this system by replacing the various various members of this Huesler family of materials. So they have a substantial magnetic field tuning. And now depending on which nodal line we are forming, we can have a different surface connections. For example, in this conventional ring, this area is gap. Whereas in case of Hopf link, the surface tip transverse across this whole range, which gives their own unique set of properties. For example, if we consider for this particular paper, cobalt, manganese, gallium, it has a very large Hall response. And it has been discussed in this talk earlier by Professor Manna. Yeah. Now, apart from this one, we have another family where we have cerium, aluminum, silicon class of system, where this cerium can be replaced with other rare earth to realize a vast family of materials. I'm specifically discussing this because it's the first non-collinear ferromagnetic Weyl semimetal. And here the Weyl node separation can be tuned with magnetism. If we just look at band structure without spin orbit coupling, it has some nodal lines in up and down spin channel. If we include spin orbit coupling, obviously along high symmetry direction, there is a gap at each point. However, if we scan in a whole brilliant zone, it gives us 24 Weyl nodes, which is similar to tantalum arsenide class of systems. And moreover, while lower the temperature, one can see this tuning, which we have actually verified this aspect now, and the paper is more or less finalized, but I haven't shared the results. But the point is, just by changing the temperature, one can tune the separation between Weyl nodes using this fashion. One of these things, although topological semimetals gives us that substantial magnetic tuning, but they still have associated trivial pockets with them. So it's very difficult to isolate the transport phenomena associated, exactly associated with the topological states. So we then start looking for insulators. Of course, the work of topological insulators start well before these topological semimetals, and how to really magnetic version of a topological insulator in 2D is a quantum anomalous Hall insulator. And the earlier version, if we consider go before the discovery of quantum Hall state, then the Haldane model actually proposed a quantum Hall state, but without external magnetic field by considering the honeycomb model. But this model is too specific, too special in the sense it's considered the nearest neighbor hopping, whereas in materials that go much beyond that. However, but that gives us a way how to realize a quantum anomalous Hall state. So if we start from just a quantum spin Hall insulator, which is having a bulk valence band and have a two counter propagating edge states, if we suppress the one edge, the spin polarized edge state like this, then we can realize a quantum anomalous Hall with the helical edge channel. I don't know why it's still okay. Sorry. Yeah. So in order to realize this topological magnetic insulator, there was two different methods. One is one can find materials with intrinsic magnetic order, or we can generate the magnetism in the existing topological insulator. The first method, by magnetic doping of a topological insulator, basically already realized in this is a topological insulator. If we add a magnetic impurity in it, there is a exchange gap open, and then system have a gap here, a gap rise in the Dirac point, and one can realize a 1D conducting gas state. And this has been verified by in 2013, which gives one first example or the first verification of quantum anomalous Hall system. This is the interesting panel which shows this is a longitudinal conductivity which goes close to 0. And whereas at that point, this transverse or whole conductivity is saturated to quantized value. So this is a smoking gun signature of a quantum anomalous Hall system. But one can see it has a very low operating temperature of 30 millikelvin. And moreover, one has to fine tune a very complex composition. So then over the year, this research grows and people start finding intrinsic topological insulators. And now already it has been realized extensively in various intrinsic magnetic insulators. The first example is MBT124. This is basically a bismuth telluride and then combined with MNTE system. And it forms a septuple layer. And over the surface, by just measuring this surface states, we find a clear gap. So although this intrinsic magnetic insulator has been determined, verified, and in the follow-up paper, there is another paper appeared that shows this surface state is gapless. Now, gapful or gapless is still a question, but just by using the various layers of this intrinsic magnetic topological insulator, one have determined a quantum anomalous Hall state which have a high operating temperature going from 16 Kelvin to 6 Kelvin under magnetic field. Our work, as well as we showed a new Hall effect, a layer Hall effect in 6 layers, where the anomalous Hall response stays up to 14 Kelvin in this paper. And there is we are also have many other works, but in this case I will move to another family, because this particular family of Zintal materials, we was working around 2019-20, same time during this material appears, but by my movement the work slowed down, but it's already now under review. The point here we were trying to say is we have to find a material having both magnetic and non-magnetic members in the same family. And this strontium indium class has actually that. So if we consider a non-trivial system, consider just a strontium case, which is a non-magnetic, then this strontium can be replaced with europium and then with various magnetic order, and one can realize this tunable state, which I'm going to discuss now. Okay. So let's look over this, how this matrix varies while changing the magnetic ordering. If we consider this strontium indium arsenic, which is a non-magnetic, but the important one of the important one of these important of course for this Zintal material is they have both ionic as well as ionic bonding in the same lattice. So it has this indium arsenic which is represented by this one is a negative state which has a tendency to take electron, and strontium is in 2+ state. So this can clearly form a charge valence insulator. So system can either be insulator or a very small gap semiconductor or semi-metal. But looking over its symmetries, we can see it has a non-magnetic space group is 194. So I'm just focusing on 3 particular symmetries, or it has more. It has inversion symmetry, it has time reversal, as well as this mirror as MZ. If we just try, this can be transverse. If we include this CAFM, which is antiferromagnetic ordering, which is already verified in this europium-indium arsenic system, then its symmetry is reduced to this 194268. If we just look for this one's, inversion symmetry is intact, whereas this time reversal symmetry is modified to a new operator, which is time reversal times this ordering vector or the antiferromagnetic vector. And
you have 6 minutes.
Okay, sorry. Yeah, sure. I will try to wrap up. And then MZ is absent. Whereas if we consider the ferromagnetic ordering, this mirror is present, but now we don't have a time reversal symmetry. Now, just by looking these different members, we can expect, like, since symmetries are different, their topological states will be different. So now in this europium-indium system, which has been very recently proposed or experimentally realized a tunable system, it has antiferromagnet with this Weyl temperature is roughly 16 Kelvin, whereas the small anisotropy between in plane and out of plane, and easy axis is in plane. So this is already experimentally verified now. So let's go with this strontium-indium quickly. If we look over its band structure, there is a clear band inversion at gamma point between indium S and arsenic P states. If we look closely over this in a whole brilliant zone, we find they form a loop in the full brilliant zone. And if we switch on the spin orbit coupling, the nodal loops gap out and system transition to a topological insulator. We also calculated the mirror chain number, and it has a mirror chain number 1, which is similar to actually bismuth selenide or bismuth telluride class of system. So this is a dual topological insulator having both strong Z2 as well as the crystalline insulator. And if we look over surface, since it's a nodal line semimetal, we can clearly see a drum head states, which is actually filling the loop over the surface. And if we go for various other directions, if we include spin orbit coupling, then this drum head state gap out, and we can realize a Dirac point over surface. If we move to another low energy surface, we can have actually the anisotropic Dirac dispersion. So we can have a carrier tuning in it, this system. Now, if it moves to the other member of europium-indium arsenic, we clearly see there is a band inversion between indium S and arsenic P, which is similar to strontium case, but additionally the system is antiferromagnetic. And obviously now symmetry is reduced. We have something is a topological insulator in a magnetic system. So if we look over again, if we just try to again looking over the symmetries, if we consider in a non-magnetic system, the state is two-fold degenerate. And due to this mirror symmetry, these points is hinges over kz is equal to 0 plane. In this particular state, the system is still a nodal line semimetal. However, the state is protected by S time inversion, but not by mirror. So basically that unhinges the state from kz is equal to 0 mirror plane. And since inversion symmetry is protected, we can rather define this G4 invariant, which gives us an action insulated state within the value. Now, if one of the biggest challenges we always encountered while dealing with the magnetic system, we see how robust do we have this state. Obviously, one can change the Coulomb repulsion U parameter by looking over that, but we have in parallel goals to consider the hybrid function, and we can clearly, without any U parameter, we can clearly see the bands, the inversion stays there, as well as this, this is with U5 electron volt, and this is without U, and one can clearly see the role of europium F state is just to provide the exchange coupling. So this state is quite robust, and considering its surface state, now something we can notice clearly is state which is not lying at the gamma point, but is moves away from gamma point to lie along a mirror line, which is shown by this dashed line and brilliant zone. Whereas if we go to another case of out of plane magnetic axis, then the surface state is clearly gapped, and we basically realized an action insulator or the higher order topological insulator state. Okay. So the subsequent, obviously one has to verify if this claim is true. The RPS measurements are performed by Madhav, Newpen's group at UCF. So this is our calculated maps for non-magnetic, which one can consider above 12 Kelvin because the Neal temperature is roughly 16 Kelvin. There is a change in the band ordering. One can clearly see splitting as the temperature is lower down. And in first principle calculation, while there is a in non-magnetic with high symmetry, we can clearly see degeneracy. There is appearance of additional state. Since the Dirac node or whatever lies above the Fermi level, so we cannot clearly verify if states is gapped or move away from the high symmetry point, but it's clear like system has a non-trivial ordering, and this has been verified various other groups as well. Now, if we move to another member by replacing arsenic with phosphorus, we can clearly see it's a band gap insulator. If we just consider the ground state and surface state, one can clearly see a gap. However, if we just try to apply a magnetic state, try to model it, we can clearly see due to large exchange coupling of europium F state, the up spin channel, they cross with each other and form the single spin channel band inversion. And due to symmetry, since there is no mirror symmetry in this particular case, we realize a Weyl semimetal, and it's an ideal Weyl semimetal, which is this proposed we are looking for from a long time with just two Weyl nodes lying along in the plane, and it's associated the chiral estate, sorry, helical estate, sorry, chiral, and this is associated the Fermi arc surface state with the top and bottom surface. If we go for change the magnetization to out of plane, we can see now the mirror symmetry is restored, and we realize actually a Weyl nodal line, or we can call a single spin channel nodal line. So now clear question arises, how so easily one can tune this, because sometimes system are too hard and because they respond very slowly to external magnetic field. And in order to check, we find out our total energy calculation shows in antiferromagnetic state, the anisotropy or the energy between EZ and out of plane is very small, it's very negligible or even less than 1 MeV, whereas in particular case of ferromagnetic, to antiferromagnetic, the energy difference is 1 MeV per europium atom, which is very small and easily tunable by external magnetic field. Then similarly, this is a phase diagram, and while scanning or preparing this talk, I recently comes another candidate with the similar physics, which just published a few days back. That also shows experimentally a similar tuning, but for another system, this alpha europium P3. So this kind of fine tuning is accessible, and we are looking forward to have it with this one. Apart from the magnetic tuning, one can also change this, tune the arsenic and phosphorus concentration to realize a fully tunable state from one end to other. So as we just discussed, europium AS case is a band inverted state, whereas P is an insulator. So one can just tune to realize a phase transition from trivial insulator to a non-trivial magnetic topological insulator. So we have substantial magnetic tunability in this material family. So while considering the various possibilities, we realize like this particular Intel material, they have various kind of topological states, a zoo of topological states, and one can actually realize that. With that, let me summarize my talk. I briefly goes through how crystal symmetry and magnetism couples together in solids to give new physics and phenomena. And I proposed isostructural and isoelectronic members in with both non-magnetic and magnetic members, and consider two distinct family. One is topological magnetic semimetals, and other is this strontium indium arsenic class of materials. A more overview is recently we summarized on invited perspective on topology and symmetry in quantum material, which will appear in advanced materials soon. I hope to look at. With that, thank you all for listening, and I'm okay for questions.
Thank you, Professor Bahadur Singh. Now talk is open for the question, comments. Please go ahead. Please raise your hand. Yeah, Kalaba, please go ahead.
So this you have talked about this role of electron correlation.
Right.
So how this correlation is influencing the symmetry? I mean, is there any anything?
Okay, that's a very nice question. So here in this particular sense, we are still in a single particle limit. And I would say correlations in that sense is not affecting the topological state. Let me go back. Yeah. So if we just look over, changing U is basically delocalizing the electron. So that changes the location of the European map states. Other than that, because the bands around the Fermi level are coming from indium and arsenic states, so it's not changed. And moreover, it's not changing the symmetries. If you are also, I think if you are referring to this particular case of how correlations one can go from ferromagnet to antiferromagnet, then definitely there is a change in symmetries.
Okay, so that's basically via magnetic alignment, but otherwise, yeah.
Yes, yes.
Okay, I am.
Yes.
Okay, thank you.
Can I ask a question, Manu? Okay, so this europium indium to arsenic 12 also resembles something like europium iron to arsenic 2. So why, I mean, the structure wise, everything looks same. So why this shows like no topological properties, whereas europium iron to arsenic 2, I don't know whether somebody has shown topological properties there in that material.
I couldn't get your question correctly. So you are comparing europium with europium Indian arsenic with europium iron arsenic, or?
Yeah, exactly. That's the point.
Oh,
Yeah.
I see. I specifically don't know much detail of the iron case, but yes, there are 1 to 2 system which are currently many people are looking, and obviously depending on the magnetic as well as the lattice, the symmetries changes. As for example, in this case, I am looking for this particular space group, and if we just change the magnetization direction either in plane or out of plane, there are certain symmetries which changes with magnetization. Now, depending on that, one can have those states. And another thing is obviously how easy one can grow the single crystal so that one can test them. So in that case, I think more people are looking for the single crystal in 1 to 2 family with the space group 164, if I remember correct.
Okay, yeah, thanks.
Maybe I can just make a comment, Bahadur. I have a feeling that one is that, of course, the structure has slight difference. Another is that indium, probably the spin orbit coupling effect is different compared to the iron, isn't it?
Yeah, that's true. But moreover, if you see, we go with the europium to iron, then both europium and iron are most of the time magnetic. And if we just look over the simple band structure, while the near states is coming from the indium and arsenic, in that case, this becomes a more, it may be a more, having many other states, not only the band inverted states. Yeah.
Yeah, the different states are contributing, and the spin orbit coupling also is.
Okay.
Yes.
Indium is giving more spin orbit coupling.
I think so, and also the states at the Fermi level.
Okay.
Iron P is there.
Yeah.
Yep. Iron D.
And yeah, just to make one more thing clear is where we are looking mostly, we look over a system which should be more like an insulating state and have a more band overlap. For example, this gentle material is most like an insulator in literature, or very small band gap semiconductors. So our idea was in 29 or other time just to look over these materials so that we can realize the band inversion easily, similar to bismuth selenide class of systems. Yeah, whereas if we move to iron and other material, of course, one have more room for electron correlation, but then system becomes more complicated.
Yeah, okay. Professor Nitesh, please go ahead.
Yeah, so it's a very general query actually. So in the case of nodal loop, if you apply spin orbit coupling and when you open the gap, so do you still expect to see any drumhead surface state?
Definitely no, because drumhead is something which is tied up to the nodal line. Okay. So for example, here, that's why specifically a nodal line is the invariant associated is basically a winding number, which is associated calculating the non-trivial Weyl phase. Because of that, we have this drumhead surface state. But as we include the spin orbit coupling, obviously this drumhead state evolved to a Dirac cone state. But these two states of valence and conduction ones really not stick together to realize the drumhead. So that's here I've written no SOC, we have drumhead, but with SOC no. They are moves to Dirac cone.
So this is very general. If you open a gap, you don't get a
yes,
drumhead.
yeah, I mean, that's exactly, because nodal line, although they are the parent to many of the states, but they are really very fragile objects. Whereas if we consider the magnetics, for example, this particular case, these states are protected by mirror symmetry. So now we have a drumhead state. So this will stay because in this particular state, we have single spin channel and there is nothing, even we include spin orbit coupling, nothing will hybridize this crossing point. So and that indeed was the case of cobalt, manganese, gallium, which was realized experimentally as the topological. Yeah. Yes.
Okay. Yeah. Okay. Thank you.
Okay. Sudipta, please.
Yeah, I have two questions. The first one is that if a say two-dimensional system has a nodal line, now can it be trivial nodal line?
Okay. That's a good question in the sense if we go with that, whenever we are talking about the band inversion, definitely there should be associated state because this cannot just jump into anywhere. So in that sense, it should be a non-trivial system. Okay. But now it also happens like you will have or maybe associated other nodal lines. So two states will combine together and give us a trivial state. What I'm trying to comment, whenever we have the band inversion, then there should be associated non-trivial state.
I mean, can there be a nodal line without band inversion?
Can there be a nodal line without? Of course, if we go for a non-symmetric symmetries, you can have a nodal lines without band inversion, and that actually happens. We call them here that we are all symmetry protected nodal lines, where we have non-symmetric symmetries. Whereas in this particular case, I am picking up just the band inversion nodal semimetals. But yeah, your answer is yes. If without band inversion, we can have a nodal line semimetal, and then one has to look for non-symmetric symmetries and go to zone boundary planes in materials.
Okay. My second question is more technical. Suppose we use normally the GGA potential is used in the DFT calculations, right? Now, in which cases you think, or have you encountered situations where there was a band crossing and it became a band gap if you go to the hybrid potentials?
Okay, that's a nice question. And being in any first principle, we always have to verify. I would personally, if I go myself, I always go to verify with the two different functional, and not means just different implementation, but just one hybrid or one is just LD or ZZA level to check the robustness of states. Because these, and we know DFT underestimates the band gap. So this thing we have to make sure. And this indeed, we found many systems which are topologically in one functional that comes out to be non-trivial, whereas other it is trivial. Because it's just we just consider, for example, we are looking over this lab. If there is a band, the band gap correction maybe unlock these nodal lines because these are anyway is accidental crossing, not the symmetry enforced, which is the case of our non-symmetric symmetries.
So in that case, you will trust more the hybrid potential, I guess. The result.
I mean, sometimes hybrid potential also overcorrect these states. So it is a very informed choice by working with experiments and theory. So sometimes hybrid correct nicely, sometimes it's overcorrect. I would say that's my personal experience.
Okay, okay, thank you.
Yeah.
Okay, so I think if there's no other question, okay, please go ahead. Now we
context, have you ever tried the scan potential, the newly introduced, which of Solon uses quite a lot?
Yes, yes, definitely. I am actually trying both scan as well. But scan, sometimes with complicated magnetism, it's coming out to be correct. But if we consider specifically the ferromagnetic case, then it sometimes fails. Whereas antiferromagnetic system, it's having the accuracy similar to hybrid functions. That's my personal experience, and we are using it extensively.
Because my concern is, of course, the hybrid is supposed to, it was engineered for insulating or semiconducting. So if you try to apply it for this semi-metals, I don't know how good it will work.
You mean this hybrid?
Yeah, yeah.
Yeah, I mean, that's the point, but sometimes that's why I was always testing with the two different functional to check the robustness of the states.
Okay, thank you.
Thank you. Okay, let me stop sharing. Okay, so we have running. Okay. So do we have other question or sorry?
Yeah, if there is no other question, let's thank Professor Bahadur Singh for excellent talk.
Thank you.
Okay.
Before we move on to our next talk, it is requested all the speakers and participants to switch on their video so that we can take a quick snapshot.
Okay.
Kindly switch on your video.
Somehow our hall is very empty. On the first day, it was much more filled up.
Yeah, we should have done that in the first day itself.
Not first day, first session.
Right, right.
Yeah, please switch on, everyone. Please switch on your video. Yeah, I mean, please go ahead. I think those who are not switching on, probably they have some problem with the video.
Yeah, I find many have switched on, but I don't see them.
Yeah.
Is there a problem?
Yeah. Devlina, please take the whatever is.
Devlina, I find many have switched on their video. It seems to be on, but I can't see them. What is the problem? I see only myself.
No, but we see many people. We see many people. Oh, you have to go to the gallery view. So there you can see lots of people. Yeah. So Devlina, is it done?
Done. Thank you.
Yeah. Okay. Thank you very much. Yeah. So our next speaker is Professor Nitesh Kumar from SN Bose Center, and he's going to talk about electrical transport of some topological ferromagnets. Professor Nitesh Kumar, please go ahead.
Yeah, so let me first share. Yeah, just a minute.
No problem.
It's not allowing me to share.
Devlina, please allow, give him the permission, please.
It's allowed.
It's allowed.
It's allowed? Okay, just let me see.
Yeah, it's coming.
Can you see?
Yeah, yeah. Please put it in the full screen mode.
Do you see the full screen?
Not yet. Yeah, now it is.
And it is moving, right?
Not yet. Please move. Yeah, it's moving. Yeah. Yeah,
it's moving, right? Okay.
Yeah.
Yeah. Great. Yeah, can I start the talk?
Please go ahead.
Yeah. Thank you. Thank you. Good afternoon, everyone. And it is my pleasure, and I'm very thankful to the co-organizers who encouraged me to give a talk at this excellent platform, because this has been attended by many well-known scientists in the community of topological materials. So today I'll just talk about some of the electrical transport measurements which we carried out in few topological ferromagnets. So I have studied many semimetals, topological semimetals, but I'll be restricting today only to ferromagnetic semimetals. So the plan of the talk is to introduce these ferromagnetic semimetals and then give you some idea about the importance of nodal lines in these ferromagnetic semimetals and how do we understand and in a way that how to enhance the occurrence of these nodal lines. For example, in flat band systems or by introducing more and more mirror planes. Okay, so just let me start with introduction. So as you all know, and because this is the last talk and many speakers already have introduced these semi-metallic states in their introduction, so I'll be just very brief. So you can see here, as you know, Dirac semi-metal is a kind of semi-metal where you have a linear crossing, and these crossings are four-fold degenerate. But if you think in a ferromagnetic material, these semi-metallic Dirac semi-metallic states are not possible because the bands are in the non-magnetic system. In the magnetic systems, it's too singly degenerate, so you will not hope to find any Dirac crossing in magnetic materials. But in contrast, Weyl semimetals could be found in either non-magnetic or magnetic materials. For example, in a non-magnetic material, if you have broken inversion symmetry, then you find pairs of Weyl points. Or if you break time reversal symmetry, for example, in a ferromagnetic material, then you also get Weyl crossings. And the other next kind of semimetallic states are known as nodal line semimetals, and these are also these can also be found in both non-magnetic and magnetic systems. If you have a non-magnetic system, then these crossings, which are present in a line rather than on a spot, so you can have four-fold degenerate lines if you have both time reversal symmetry and inversion symmetry present. For example, in the case of zirconium, silicon, sulfur. But if you have a non-magnetic system, but the inversion symmetry is broken, for example, in lead tantalum selenide, then you have a two-fold degenerate nodal line. And also in the magnetic system, you will always have this two-fold degenerate nodal lines. And if we compare the non-magnetic Weyl semimetals versus the magnetic Weyl semimetals, the main difference which comes here is that in most of these non-magnetic Weyl semimetals, you will have your opposite chirality Weyl points are at the same energy level. Okay, and this is true for most of the non-magnetic Weyl semimetals. For example, type 1 Weyl semimetal. But in type 2 Weyl semimetal, you could also have this energy difference between these two oppositely chiral Weyl points. But in magnetic Weyl semimetals, it's almost always the case that your opposite chiral Weyl points are present at different energy levels. Okay, and this is very interesting. If you have one of these Weyl points occur in the below the Fermi energy, and the opposite chirality Weyl point is above the Fermi energy, because now you could have a net Berry curvature, okay, in a magnetic Weyl semimetal. But in the non-magnetic Weyl semimetal, because these are at the same energy, the total Berry curvature, if you sum over Berry curvature in a Brillouin zone, it will be a net zero Berry curvature. And most important feature of transport properties, if you see in a topological semi-metal, the most important feature we observe is anomalous Hall effect. Okay? In order to understand this, so you can always compare these feature-wise, at least with a magnetic data. For example, if you have a soft magnet, you will have a saturation magnetization without any coercivity, but in a hard magnet you can see there is a coercivity and you have a saturation. Okay, and because of that you have some remnant magnetization. And if you correspondingly go to anomalous Hall data, you will see that the feature is almost same, but there is some difference in the saturation limit. So you can see here either it can give you a negative slope or a positive slope, and depending on whether the charge carrier is positive electron type or hole type, these slopes will vary. Okay, and these are from the ordinary Hall effect. But you will also see that at zero magnetic field, you have a finite Hall resistivity or conductivity, and this value is called anomalous Hall conductivity or anomalous Hall resistivity. Okay? And there are various components of anomalous Hall resistance. For example, as I told you, it can come from a very trivial Lorentz force. Okay, and this R0 is in that case is the Hall constant, normal Hall constant, but there could also be contribution from Berry curvature. Okay, and the second term which is shown here, let me just. Okay, the second term, this RS is a coefficient which contains all the information of Berry curvature. If we are talking about intrinsic anomalous Hall conductivity, then this coefficient is very important to understand what is the anomalous Hall conductivity. Okay. And in experiments, if you measure Hall resistance and longitudinal resistance simultaneously, then you could always, because of this is a tensor quantity, you could always calculate this Hall conductivity with this relation. And as I told you, anomalous Hall conductivity, the reason behind the anomalous Hall conductivity, I'll discuss and mostly confined to the intrinsic effect, and it is related to the Berry curvature. And the Berry curvature, from this Berry curvature, you could always have the value of anomalous Hall or the Hall conductivity by this theoretical relation, where you can see that you have to integrate this Berry curvature in the whole 3D build-on zone. Okay, and with this Fermi function multiplied here inside the integration. Okay. And there's a very interesting symmetry. So for inversion symmetric systems, we'll see that the Berry curvature at a particular k point would be equal to the Berry curvature at a minus k point. And for a time reversal symmetric system, it will be minus of the Berry curvature of at the minus k point. So if you have a system which has both inversion symmetry and time reversal symmetry maintained, then you don't hope to get any net Berry curvature. Okay, so in order to have a Berry curvature, you must either break a time reversal symmetry or an inversion symmetry. And in order to get anomalous Hall conductivity, you should always work with magnetic materials, because you are measuring the Hall resistivity, and the time reversal symmetry must be broken because you are measuring Hall. Okay. And this is in the right hand side, you can see it's a very simple two-band model calculation, and you will see that if you have anti-crossing between these two bands and you calculate this Hall conductivity, which is done usually using the Kubo formula, which is related to this expression which I have shown here. So you will see that if you go within this gap, then your Hall conductivity peaks out. Okay, and it almost remains constant within this gap. And if you go above, then it goes away again. So what you need then is to find these anti-crossings in your real materials. Okay, and these anti-crossings would be more pronounced if you have a nodal loop kind of scenario in your compounds. So this is a very simplified cartoon picture. You can see here that without SOC you have a nodal line, but when you apply an SOC, then you'll see that you have a finite band gap, finite gap. Okay, and because of this anti-crossing, this is the hotspot of Berry curvature. So if you see here that if you find the hotspot mainly in the confined region of this anti-crossing, then you must have many nodal lines in order to have increased Berry curvature effect. Okay, so in real materials, we'll always look forward to get as much as possible nodal lines. So one of the most important results in this class of materials came in 2015, when Nakatsuji and the group, they discovered a very large anomalous Hall effect in manganese 310. So if you see the magnetization measurement, so the magnetic moment of the material is very small. And the earlier belief was that if you have a very small magnetic moment, so your anomalous Hall conductivity should be very small, because earlier people thought that this anomalous Hall conductivity was directly related to magnetism, and they did not know about the effect of Berry curvature. Okay, but in this system, even if the magnetic moment is very small, you can see the anomalous Hall conductivity has a very large value, and this has been attributed to mostly because of this Berry curvature effect which the system has. Okay, and very soon Nayak et al. So the last day's speaker Ajay Nayak, he measured this kind of anomalous Hall conductivity in a very similar system, which is manganese-3 germanium, and he could see that the effect is even larger in manganese-3 germanium compared to manganese-310. Okay, and if you see that in the theoretical studies, they find that there are hotspots of Berry curvature in the Brillouin zone, and these are these large anomalous Hall conductivity is directly related to these kind of Berry curvature hotspots. Okay, so the first example which I am going to show you today is of a Kagome ferromagnet, which is a Weyl semimetal, and this is a shandite compound, which is cobalt-3 Sn2s2, and this is a very large family of compounds, because instead of cobalt you could have nickel, iron, and instead of tin you could have indium, and instead of sulfur you could also have selenium. So this is a very large family of compounds, but this compound is very unique because this is the only compound in this series where you have metallic conductivity, and you also have a ferromagnetic magnetic structure. Okay, so this system has a if you see the structure, it has Kagome lattice of cobalt atoms. Okay, and the spins in these cobalt atoms, it is out of the plane. Okay, and if you see the so this compound we prepared by, so this can be actually prepared by many ways. You can prepare it either by normal congruent melting, or you can use excess tin flux, or you can also do this by chemical vapor transport method. So this particular crystal was like made by congruent melting of these individual atoms, and this is a single crystal XRD diffraction. You can see very nice spots, which that's a very nice single crystal. Okay, and when you see the band structure of this compound, so without spin orbit coupling, you'll find there are some crossings. Okay, in the red you can see red lines, but when you apply spin orbit coupling, so these crossings are gapped out. Okay, but these crossings are not gapped out everywhere. That we'll see in the next slide. Okay. First of all, we'll see some of these electrical transport properties of this compound. So first of all, I told you this is a metallic compound. So if you make a resistivity measurement, you see that the resistivity goes down with temperature. Okay, and there's a kink here in this resistivity, which is corresponding to a ferromatic to magnetic transition. Okay, and if you do this magnetic resistance measurement at very high magnetic field, so this was done up to 35 Tesla, you will also see some ripples here, and these are quantum oscillations. So because we have quantum oscillation, and if you remove the background, you have a nice quantum oscillation, which is periodic in 1/b. Okay. And if you use the Onsager relation, so you could always convert this frequency to the area of fraction of this Fermi surface. And this data tells us that the frequency should be around 197 Tesla or around 200 Tesla. And when we see from these calculations, the extremal orbit cross section is also around 200 Tesla. So this is a very good match. And from here, it indicates that you have semi-metallic kind of system at your hand, because you could see there are electron pockets and hole pockets. Okay, but there are many electrons and hole pockets, but we only see one frequency here. So maybe if we go to even higher magnetic field, then we could also deconvolute other frequencies related to other Fermi pockets. And the semi-metallic nature also has indication from this magnetic resistance plot, where you'll see that magnetic resistance increases and does not saturate even up to 14 Tesla. And moreover, in the Hall data, you will see that in the saturation limit, the Hall resistance first decreases, then goes to a minimum and it increases. It means there is a positive, negative slope first, then it is a positive slope. It means that you always have electrons and holes together in your system. So it also indicates it's a semi-metallic compound. And as I told you earlier, it has a crossing in the band structure, and these crossings are actually nodal loops. So this is a representation of these nodal loops. This is a part of the band structure. Okay, and this is without spin-orbit coupling. But when you apply spin-orbit coupling, so these nodal loops are actually gapped out, but not at all the points. So at some point, these are all still degenerate, and these are the Weyl points. Okay, and there'll be anti-crossing in all other places, so which can give you very large Berry curvature effect. And if you project here, you can see that it indeed gives you a hotspot of Berry curvature in the Brillouin zone, and which would correspond to large Hall conductivity, which you can see here at Fermi energy could be around 1000 ohm inverse centimeter inverse anomalous Hall conductivity. And when we measured this compound, then we indeed see that it has a very large anomalous Hall conductivity, which is around 1000 ohm inverse centimeter inverse. So which means that it is almost always intrinsic contribution in the anomalous Hall conductivity. Okay, and as you go to higher temperatures, above the transition temperature, you obviously kill all these anomalous Hall conductivity effects. Okay, so this was the story about cobalt 3s and 2s2, but at that time we were looking for some layered compounds, because there are very few van der Waals materials which are layered ferromagnets. So we were looking for alternatives. For example, whether there are systems where we have magnetic layers which are separated by non-magnetic layers. So in principle, these are three-dimensional compounds, but magnetically it could be two-dimensional. So one of the ways is to just, for example, to start with the Heusler compound. Okay, and yesterday also we saw, and today's talk also we saw that in a Heusler compound, it's very like anisotropy is not present. So it's very easy to align the spins in any direction. Okay, it does not prefer any particular direction. So if you remove some of these tetrahedral interstitials, for example, alternatively removing some tetrahedral interstitials, you end up with a structure which is PPFCl structure. Okay, which is the which is a version of Cu2sb type structure, and this structure is similar to what we get in manganese, aluminum, germanium. So it's a tetragonal kind of structure, and this is a very interesting structure because you have a manganese square net here, and this structure is very similar to iron-based superconductors also. Okay, and you can see here these manganese layers are separated by non-magnetic layers of aluminum and germanium. So we expect that there would be some kind of two-dimensional nature of magnetism here. Okay, in order to appreciate this two-dimensional nature of this compound, we have compared it with some other compounds. So here you can see D is the distance between two magnetic layers. So this value is 5.93 angstrom for manganese, aluminum, germanium, and which is like comparable to systems, for example, van der Waals systems, which is intercalated by iron, okay, which is also around 6. But it is still smaller than these van der Waals compounds, which is a ferromagnet Fe3GeT2, but again bigger than this last example which I gave you, cobalt, tin, sulfur. So we wanted to understand the electronic properties of this compound. So Dr. Jansson did this first principle calculation for this compound, and we saw that there are some nodal lines which appear above the Fermi energy. Okay, and if you apply spin-orbit coupling, these nodal lines are gapped out. Okay, and when you consider these bands which are responsible for these nodal lines, so you get this kind of Fermi pockets which are contributed from bands which take part in the nodal lines. And and if you also see the Berry curvature of this compound, then you'll see that there's a one-to-one correspondence of these Fermi surface and the Fermi pocket and this distribution of Berry curvature. And you'll see that this is a first example of two-dimensional kind of Berry curvature distribution. But one problem we have here is that the nodal line is above the Fermi energy, and we wanted to check it with the RPS measurements. And when we did the RPS measurement, we found that this, because of the self-doping in this compound, this Fermi energy actually has been pushed up, and you will find these nodal points below the Fermi energy. And we also see some surface states, but we are not very sure whether these surface states are topological surface states or not, because at least these are surface states, because they are not matching with the bulk states. Okay, and because now this nodal crossing is below the Fermi energy, and then you expect to get a very large anomalous Hall conductivity, which is around 700 to 800 ohm inverse centimeter inverse. And when we do the measurement, the transport measurement, we indeed find that the anomalous Hall conductivity which we get is around 700 ohm inverse centimeter inverse in this compound. And it's very interesting here, because once you have a bulk anomalous Hall conductivity, you could always calculate what is the contribution from one sheet of this manganese layer. And when we do that, we'll see that it is around 1 E square by H. So in that sense, it is like a stacking of channels, this quantum anomalous Hall channels in the C direction. Okay, and this is very surprising, because you also see this kind of effect in Fe3GT2 and Scobol3SN2H2. We still don't understand it completely, why it could be. It's just a coincidence, or it has some deep meaning, why it is around E square by H if you count per layer conductivity, anomalous Hall conductivity. So, as I told you, we were that time we were searching for some layered ferromagnets. So we came across to a very big family of ferromagnets, which is the rare earth chromium antimony compound. And this actually has in-plane ferromagnet as compared to last two examples where I showed you the out-of-plane ferromagnets. But this is very interesting, because here also you have chromium layers, and these are separated by, again, non-magnetic layers. Okay, if you have lanthanum, then this is the separation is by non-magnetic layers. But you could always have other rare earth, for example, cerium and gadolinium, which I'll show you in next few slides. So we grew this crystal by antimony flux method, and you can see the Lowry diffraction pattern here. Okay, and this beam is along B axis, and the magnetic structure is very interesting, because you have in plane, but these are not collinear magnets. So you will have a canting in the B direction, which is around 18 dB. And the most important thing in this compound is that you have some kind of flat band kind of character near the Fermi energy. So you can see here, these bands are very flat near the Fermi energy. And if you calculate the Berry curvature, so you will see that there are many crossings which are giving you Berry curvature near the Fermi energy. Okay, and this is just a way to see the bands are really flat. So this is the middle thing is the curvature of these bands, and the corresponding Fermi corresponding Berry curvature is at the bottom. And you'll see that the regions where the bands are flat, you also have these hotspots in the Berry curvature. And at the edges also, the bands are more or less flat, and you have a large Berry curvature around the edges also. And in the experiment, when we do the transport properties, you see that you have very large anomalous Hall effect if you have your magnetic field around B axis. So as I told you, in around B axis is the net magnetic moment is finite. So you have very large anomalous Hall conductivity when you have magnetic field aligned along the B axis. This is the green curve. You can see the magnetic field is applied along the B axis. And if you apply the magnetic field along C-axis, then you see that in C-axis the net magnetization is 0, so it's kind of antiferromagnetic kind of interaction along C-axis. So initially you will have no anomalous Hall conductivity, but when this scanting is overcome by a finite magnetic field, then you will have a sudden metamagnetic transition and you have very large anomalous Hall conductivity. So it again tells you that the antiferromagnetic spins don't give you anomalous Hall conductivity, but as it goes to a ferromagnetic kind of situation, you have a very large anomalous Hall conductivity, which is like 1-to-1 correspondence with the magnetic data, which is at the bottom. Okay. Then you could also go to other rare earths. In place of lanthanum, you could have cerium and gadolinium, and we found that in cerium and actually this is not gadolinium, this is neodymium. So there's a mistake here. So if you measure the anomalous Hall conductivity, you see that again the anomalous Hall conductivity is very large for both these compounds. But here the situation is slightly complicated because of the introduction of electrons. So in neodymium case, because of additional ordering of neodymium, so we have some metamagnetic transition. But once you have a large magnetic field, then you also see very large anomalous Hall conductivity. But the interesting thing here is the anomalous Hall conductivity is not in 1-to-1 correspondence with this magnetization, which is what we expect, right? Because it should not always scale with magnetizations. For example, if you see in cerium case, so in the A direction, the magnetization is very large, but you have very less anomalous Hall conductivity. Okay, and also for neodymium case, you see that magnetization is very large along A-axis, but you have very less anomalous Hall conductivity. Okay, so there is not exactly 1-to-1 correspondence, and this is due to the very curvature effect. Okay, so these were the three set of compounds which I wanted to show you. So in the summary, I showed you that cobalt 3 SN2S2, if you have because of the nodal line contribution, you have a very large volume of Berry curvature. Okay, and this was also true in manganese, aluminium, germanium. But additionally, we saw that we had a two-dimensional kind of Berry curvature distribution, which is very unique, which has been seen in this case. And also in the lanthanum, chromium, antimony, you have a flat band kind of situation, and it enhances the Berry curvature. So flat band, what it does is like it increases the probability that you have more crossing near the Fermi energy, right? Because if it is flat, then there are chances that the bands will cross there, and you will get more anti-crossing than more compared to the dispersive bands. So we think that flat band can enhance your Berry curvature effect. And also, as also pointed out in the last talk, that if you have many mirror planes in your compound, as was also the case in Heusler compounds, then also you have enhanced Berry curvature effect. And we also saw that in some other compounds, for example, HF MNP and zirconium MNP, but I'm not discussing those compounds here. So with this, I'll thank you, and I can take any question if you have any.
Yeah, thank you, Professor Nitesh, for finishing the talk before time. Okay, so there are 2 questions already. Yeah, Gaurav and then Professor Bahadur Singh. Gaurav, please go ahead, and then.
Sir, thanks for very informative talk, sir. Actually, sir, I have a simple question, sir. What is the, sir, means crossing means when two bands crosses each other? So at that point, say for same K, that point have same K value. But sir, I can't understand exactly what is the anti-crossing, sir, which you have told here, anti-crossing of two band and large Berry curvature, sir.
Anti-crossing in the sense that there was a crossing and it was a non-trivial crossing. So you have a non-trivial, you have a topological crossing there. And if you apply a spin orbit coupling, then you open a gap there. Okay. And that is called that's what we call anti-crossing. And that gives you very large Berry curvature, because from the Kubo formula, you have that relation, right? In the denominator, you have that difference in energy. So it gives you very large.
Okay, sir. Okay, sir.
Okay.
Yes.
Yeah, Professor Bahadur Singh, please go ahead.
Thank you. Thanks, Jay, for a very nice talk. I have actually a rather fundamental question for these flat band enhancements of the Berry curvature. Although we know, like when these systems repel each other, we have a band repulsion, then Berry curvature is definitely large due to singularity. What role this flat band? Of course, you touched briefly, but I want to understand from experimental perspective how what flat band is playing a role in driving this anomalous Hall conductivity. The flat band, how flat band is relevant other than the anti-band cross.
Yeah, actually, this is not the topological flat band which Professor Barnavik and other speakers were talking, which is the case in cobalt 3 SN2S2. But in those cases, these flat bands are not at the Fermi energy. But these flat bands which we observe is not because of that topological non-trivial flatness. So these are mostly because of the localized situation in magnetic samples. So in this particular ferromagnetic systems, we saw that the band was really very flat. And because of this flatness, we think that there are chances that the density of anti-crossing will be enhanced compared to more dispersed. So in a very small window of energy, you will have more chances that your bands have anti-crossing. That's what we understand. And actually, there are no other experimental studies yet to correlate anomalous Hall and the flat band. So, yeah, maybe.
Okay.
I hope.
Okay. Professor Tanushree Sahadas Gupta.
Nitesh, nice talk. I just thought of this in the context of this manganese compound, where you had this two-dimensional distribution of this Berry curvature. Does it have any advantage in terms of the anomalous transport property?
Yeah, so this actually it's very important question. So this two-dimensional Berry curvature, this asserts here that so first of all, we wanted to show that this is a kind of layered magnetic system, because this layered magnetic system, if we have out of plane magnetization, then this could be potential candidate for achieving quantum anomalous Hall effect if you grow thin films and because of confinement you could have. So first of all, we wanted some layered ferromagnetic system where the spins are out of plane. So once we have this kind of system, then we wanted to understand if the nodal lines which are responsible for which are taking part in this nodal line, so the bands which are taking part in the nodal line, so these form this particular set of Fermi pockets, right? And with these Fermi pockets, if we correlate that the Berry curvature distribution is exactly mimicking this set of Fermi pockets, then we were convinced that the transport which is happening is due to the two-dimensional nature of the magnetism. So that's what we wanted to correlate, and which is really the case here.
The other question is that if you really have this two-dimensionality of the system, then there will be very strong influence of the fluctuation, because the dimensionality reduction enhances the fluctuation. And in fact, we showed that fluctuation can open up many different things. So, like which can be even topological superconductivity, it can open up this fractional churn insulator and all that. So, is there any kind of experiment been done on this?
No, actually, this material, actually, this was known earlier, but only magnetic measurements were done. So after that, we investigated in the context of these topological bands. So there are no other information yet available. So it will be a good idea.
Did you try to cleave this material? Is it cleavable? Like
actually,
isolate the layers?
No, actually, structurally, if you see, it is not two-dimensional, because this the separation between these aluminum, germanium, these layers, it is like very normal separation. So it is, in that sense, it is not cleavable. So structure-wise, it is almost three-dimensional. So that's why I thought that making thin films would be a good idea rather than cleaving it.
Okay, okay. Maybe we can discuss later. It looks like very interesting compound.
Any other questions?
Manu, can I ask a question?
Yeah, please.
Because thanks for a very nice word you taught. So,
yeah, thank you.
So the systems that you showed today are magnetic systems, right? So
yes.
You studied anomalous Hall effect due to Berry curvature. So how strong is the magnetism in these systems and its contribution towards anomalous Hall effect? The anomalous Hall effect due to magnetism.
Yeah, actually, anomalous Hall effect, if you have to observe, then it always have to be magnetic, first of all. So because here you see that, so this term here, anomalous Hall resistivity, this anomalous Hall part has this magnetization attached with it. So magnetic.
Yeah, please.
Yeah, so magnetic, you always need magnetic moment. So if you have a finite magnetic moment, then it depends on how much contribution is this factor RS, which has this Berry curvature information. So if you have very large Berry curvature, even if your magnetization is very small, you could have very large anomalous Hall resistance, anomalous Hall conductivity. That's what was seen in this Mn3Sn. So you can see that the magnetic moment is very small in this case, but even then you have very large anomalous Hall conductivity. So you can see here, this magnetization is around Mn3G, it's around 0.02 Bohr magneton per formula unit. So even then you get around 400.
No, my question was like you have there, right? Berry curvature times magnetization.
Yeah.
So it's a ferromagnetic system. So don't you have like a intrinsic anomalous Hall effect due to ferromagnetism rather than the Berry curvature?
So if you consider all kinds of contribution, so intrinsic contribution is always from the band structure, but you could always have those extrinsic effects. For example, skew scattering and side jump. But if your sample is not very disordered, and if you could and if your conductivity is not very like bad metal or not very conductive, so in the intermediate range, most of the times you will have intrinsic effect dominating.
Okay.
So which was most of the time true for our compounds.
Okay, thanks. Yeah.
Okay, so so Diptada, please go ahead.
Yeah, just a clarification. I wanted to ask you is why do you need magnetic materials for anomalous Hall conductivity Hall effect? I mean, it can happen in non-magnetic materials also with large Berry phase curvature.
Actually, in non-magnetic, yes, what happens, because most of the time what happens that if you have your Weyl points, for example, then these Weyl points are of opposite chirality, they happen to be at the same energy. So net Berry curvature is always 0 in this case.
But in Dirac materials or some other.
Yeah, in Dirac material also. Yeah, so actually type 2 Weyl semimetal, is one example where you could have these two opposite chirality Weyl points at different different energy. So if you can have these Weyl points, one Weyl point above the Fermi energy and one Weyl point below the Fermi energy, then you could have a net Berry curvature. Then there could be, so there are some theoretical studies which suggest that this could also support anomalous Hall effect, but in experiment we have not seen yet.
Okay, I see. Okay, thank you.
Related to this question, like Mn3Sn is known for anti-ferromagnetic system, right? It's not ferromagnetic.
Yeah.
Like anomalous Hall effect. So
yeah,
it's not due
yeah.
to.
Yeah, and Mn3Sn actually this matic structure, mostly it is reported that these spins are like on the edges, on the vertices of a triangle, and they align along the sides, but there is a net moment in one direction, even without the magnetic field. That's why you have a net anomalous Hall conductivity there. So there is no zero magnetic moment there. There is this very small net magnetization.
Okay.
Yeah, if there's no other question, let's thank Professor Nitesh Kumar for excellent talk. And with this, we end the session here, and I hand over to Professor Sethi.
So we almost came to an end, I think. Yeah, so we had a very good talks. Actually, although we did not plan like how we planned this like kind of talk. So I think we covered most of them, like we covered art based, DFT calculations, modeling. And if I see only one kind of talks that we not cover is like neutron and then thermal conductivity. And in fact, we also planned, Comrade Benier was invited and he also accepted the invitation. And last minute he had to cancel that. Although at the beginning we did not plan like it was that much diverse. And yeah, thanks a lot for the all the speakers who has given excellent talks and who made this a wonderful conference. Even before that, we need to thank Professor Sahadas Gupta to make it like hybrid. We never had an idea that we wanted to have a hybrid. When we were thinking about this conference, we wanted to have it an online mode. And the Professor Sahadas Gupta said that no, let's we had enough of Corona, so let's do it in hybrid mode. So yes, we started, and then yes, many Indian speakers agreed to come. Professor Kala also is here, so I mean, in fact, he's the only speaker who came. But actually, 15 to 16 speakers agreed to come, and it was, in fact, was going to be really like kind of physical conference. But unfortunately, there was a third wave, and then we could not, we did not dare to go ahead with the real hybrid mode. Then we again requested all the speakers who really shows, I mean, wanted to come over here. Then yeah, very third wave, not many speakers were showed interest to come over here. But by the time we start this conference, the Corona also is gone. But to arrange all these logistics, we need to have a prior plan. Otherwise, it would have been a very nice conference. So for this, let me thank once again our director, Professor Sahadas Gupta. Otherwise, it would not have been like this, the conference. And then, yeah, so there's one more team that we need to, on behalf of organizers, that we need to thank. Is the technical team, Devlina and Mithai. And there are other people actually, in fact, they were forced to listen all the talks. Even organizing members at the time actually have been to go out and come, but these people were listening all the talks and sitting all over here. I mean, all the time. We really owe a big thank to them. And then, yeah, we have a couple of student volunteers. Shweta from my group, and Manodeep is not here, but yeah, he's from Manoranjan's group. They really helped a lot. So they were actually the contacts, like they were sending the mails, and then they were actually doing all this background job. And then, are there anybody else?
May I request all the speakers and the participants to turn on their video for one last time?
You want to add anything?
Before that, may I propose to thank all 4 organizers. This was a fantastic conference in spite of all the difficulty. So please join me in virtually clapping them.
Thank you.
Can you turn on your video?
Would you like to add any more?
Yeah, I mean, we can take a feedback from some of the senior people if they want to have, I mean, we want to know their opinion and feedback. Like Kaloda, Sudiptoda, Tanusridi, all these people can give us a feedback, suggestions, right?
I think, yeah, I think from the participant side, I'd like to thank all the organizers. It's a fantastic meeting. I really enjoyed, although partly I'm here and partly I was attending from TFR. So both online and offline. I got the experience of both. So, so it was really good. Yeah, actually, I really enjoyed to be here because it looks like that almost like we are sitting in the hall and listening to talks. Although speakers are not physically being seen, but it was more like a real physical talk. So and it's fantastic. I think the organization was really good.
Yeah.
So
Yeah.
So thanks to your NET team, so, so they have done very well. So I think we should have this kind of meeting. It was very informative. A lot of participants from abroad as well as in India, and there are different topics related to topological materials, which is really the interesting field these days of quantum materials. So I once again thank you all for this wonderful meeting.
Sudipta,
yeah, this has been a very nicely organized conference, and I thank all the organizers as well as I thank Tanushree for organizing this conference, and the quality of the talks were also very nice and very educative as well as interesting. And yeah, and I look forward to such kind of conferences. I would have, I mean, I always love to come to Kolkata naturally, but could not come. But next time I will take the opportunity to come physically. Thank you very much.
Thank you. Tanushree.
Actually, ma'am's video is not showing. Shows she is reconnecting.
Tanushree, you want to have some words? I mean, is he there? Priya?
No, not much, but nothing more than what has already been said. It's a very nice meeting on a focused topic, and maybe one should plan for, have maybe a day-long meeting more times in the year just to keep updated.
Yeah, that's true. That's true.
Thanks.
Thank you. Anyone else?
Those who are online, you have missed nice food.
Yeah. Anyone else? Sergey, Professor Sergey, do you want to have some words? Anyone else wants to have?
I have one suggestion which I made right at the beginning. Please try to make this series a regular event, and you might talk to other, kind of. We should build up a kind of a knowledge base in India, because we have synthesis people, characterization people, calculation people. And like your quantum materials, this is actually a kind of a subclass of that quantum materials.
Yeah.
But it is a field by itself now. So we should try to, and also topology, for example, in classical system has become quite popular. And for example, I know that like Shubhra Bhattacharya, he is doing quite a bit of work on that. So we can have actually on the theme of topology, you can make it like a regular event. That will be very much appreciated, and that will probably help us to come up with a team of people.
Yeah, that's very good suggestion. That's very good suggestion.
Yeah.
Okay. Anyone else wants to say something? Bahadur, do you want to say something?
No, I actually agree with Professor Sada's suggestion. And while listening to all wonderful talks across the 3 days, it seems within India we have a strong knowledge base definitely on these topological materials, starting with the basic characterization analytical modeling to computations to synthesis and RPS and various other things. So definitely it's a must sorted and one can try to build knowledge base, or at least we should have a topological meeting at least on regular basis.
Yeah.
And moreover, this obviously is a part of a quantum material initiative, but that is a bigger umbrella. So one can have a focused meetings on topology. I would fully support that, and I agree.
Yeah, that's very good suggestion. Yeah, I agree with you. Anyone else? If not, then Professor T, please go ahead.
I think I'm almost done.
Okay.
Yeah. So I mean, I just want to ask any technically, what I mean, we had one problem, right? The process, this group, we had technical problem.
Yeah.
Jaime Pariga's talk, that only two little things. And it was very unfortunate to miss him. Actually, he has done a lot. I know him personally. In fact, he was my colleague, PhD colleague, Jaime Pariga. And he did a lot of art-based work on topological systems. I wanted to listen his talk, but I missed it. I don't know, somehow I could not. Maybe he was confused with the timing. Yeah, so apart from that, I think it went very well throughout the conference. So as Professor Saras Gupta said, yeah, we need to think, maybe in a more way, like we have to expand this platform all over India, and then we need to see. Yeah, that's what from my side. So
yeah. Any student wants to say something?
So you people, any comments from your side?
From online?
How many talks you attended?
No, but I see there are many people who really like they were all the time there.
Actually, my reaction is if it is offline mode, then we can catch up after talk some professor, then we can discuss lots of things.
Yeah, most of the talks will be available online on YouTube. So we need to take permissions from those who we did not take already, and then they will be uploaded in online. So you can again go through them once again, and then you can contact respective professor or speaker for any clarifications.
But I think in future they will have offline meetings. I mean, I think that's the suggestion that Professor Dasgupta said, which is a very, good suggestion. So maybe you can form a group of people and just continue with this.
This is very focused. Already we have this QMAT, I think, which is already covered.
It's very different, but this one is more
focused.
It's a good idea to have quantum materials group. I think Bahadur, if I remember correctly, Bahadur mentioned this to me at some point at
Yeah, actually we were discussing this point a bit. I mean, definitely
very active on this. So he was talking about it, like having an active quantum material group, so that you can take it forward. And have meetings and discussions and so on.
So the next meeting on our topology forum can be in TIFR.
Yeah, that's true. That's true.
Yeah, so Professor Mehti can comment more on that since I am more
Yeah, we will do it. So
maybe we can think about workshop for students, because this is a very new field. So interactive few days workshop might help.
No, that's a very good suggestion. I would also say, we'll be happy even if it is online. I think within a 6 month, if we can do something like a 1 week course kind of things, and if there are people who can really, some of us agreed to do that, we'll be happy to support. And our director is here, and I think she'll be.
Definitely. It's a very good idea, because a lot of young people are joining this field and they have a lot of conceptual questions. So having such a workshop will be very, very appropriate. And we do have experts giving conceptual talk, a pedagogic talk.
It's a good idea. So, and anyway, I think this COVID thing will go away. So we are now already used to it. So it would be offline, I think. So then
better offline, then they can interact and even after workshop time.
Yeah, I think that workshop will happen in maybe in TFR.
Fine, or maybe. But workshop is very useful for student and younger who has just started.
Just to add, I was also trying to highlight this earlier as well. We had extensive discussion with Professor Kailo as well. Now, condensed matter or material science doesn't just remain without anything. Now, current one has to add topological condensed matter and material science, which itself is a full-blown field. So, yes, in India, we definitely have a good knowledge base or the people working on this aspect. So, this kind of meetings definitely will be helpful, I would say, for students as well as for catching up with the field.
Yeah, that's true. Yeah, we can circulate an email and let's see. We'll have some kind of consensus. Then we'll organize it. What is big deal?
One of the biggest problem for longer meeting may be finding the suitable time for everyone to meet.
That's true. That's true.
Anyway, so let's thank the organizer here from our side for a nice beginning, and it was a very good meeting. So it was very interesting. Yeah.
Thank you.
I see the Sergey is still there. Oh, I see.
Thanks to Seti, he took lots of effort too.
Yeah. Hello, sir.
Yeah, Krish. Yeah, Krish.
Good evening, one and all. May I have two suggestions. May I express it here?
Yeah, please.
Sir, first of all, thanks to organizer for this very informative conference. And I have two suggestions. One is the conference, these type of conference should be in hybrid mode, so that we can attend the conference. Sometime traveling and sometime funding issues also there. And second thing is, if some workshop is code based, means then this would be very useful for some the new students.
Okay.
That's two things I want to say, sir.
Okay.
Thank you.
Okay, that's good. We will keep in mind. Thank you.
I mean, hybrid mode means these talks can be available online, like live stream, something like that.
No, I think hybrid is okay in a sense. Most of the people can come. It's always good to have the online thing, so that if someone wants to attend and they can interact, that's fine, right?
Exactly.
Some are critical. No, I mean, if somebody has difficulty, it's an option.
You can accommodate both.
So then, let's wind it up soon. Are there any other comments or suggestions?